Alright, let's go ahead and get started. So quickly recap the big idea of the last chapter, the equation that you'll be using over and over again, that you used 100 times on your homework problems. Here's our equation. Tell me what the equation says.
Your initial potential energy plus
Initial potential energy plus
the initial kinetic energy plus the work done on the system is equal to your final potential energy plus your final kinetic energy.
Perfect. And the thing that you'll screw up the most is accidentally replacing that with the work the system does rather than the work done on the system. The difference between those is just a sign. If positive work is done on the system, then the system does negative work and vice versa. Okay. And then remind ourselves of some of our basic definitions that will never go away. What's our definition of work? It's the integral from some initial point to some ending point of the force dotted with the displacement. So that gives you the work done by a particular force. If we look at the work done by all the forces, so if we look at the work done by the total force, then that always and forever gives us our change in kinetic energy. And that's what we use to derive the equations up here. Okay, in the special case, where F is a conservative force, in that special case, then when you calculate the work done by that force, you're going to get some potential energy function. And the work done by the force will always be the negative of the change of the potential energy function. If gravity does negative work, I'm storing potential energy. If gravity does positive work, I'm losing potential energy. If a spring does negative work, we're gaining spring potential energy. If a spring does positive work, we're losing spring potential energy.
Yeah.
So opposite signs of each other, and we did it specifically for the case of spring and for the case of gravity, but it's true for conservative forces in general.
Yeah.
And then we had this final equation, negative, 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 negative. If you have your potential energy function and you want to get your force vector from it, then you can always take the negative gradient of it. What's a negative gradient? The gradient is just a partial derivative with respect to x, y, and z of each of the components. And do you remember how to calculate one of those?
Yeah.
You just treat the y's and z's as constants and take the derivative with respect to x.
Yeah.
And same with that, same with that. So they're pretty easy to calculate, even though we haven't really done a lot of calculus with partial derivatives yet.
Right.
Okay, so that's a quick recap from the big ideas last time. Any questions before we jump into today's material? Okay, so jumping into today's material, the chapter is all about momentum. And it's an extremely useful tool. Just tracking the energies, which is what we were doing before, it turns out can be extremely difficult. Just using energies to try and figure out how some object is moving.
Correct.
So, for example, imagine that I tell you there's a block of wood right here, and I'm going to shoot it with a bullet. I tell you the speed of the bullet, and the mass of the bullet, and the mass of the block of wood. I want you to calculate how that block of wood is going to move once a bullet hits it. That, on the surface, seems like an extremely difficult problem, and how on earth would you do that? Tracking the energies, in that case, is extremely difficult because a ton of energy is lost. When a bullet goes into a block of wood, the kinetic energy of the block of wood after is much, much, much less than the kinetic energy the bullet had before it went into the block of wood.
Right.
And where did all that energy go?
Heat.
It went into heat, into the actual deformation and breaking of chemical bonds inside that bullet as that bullet injected itself into the wood.
Right.
And so we lost a ton of energy drilling into the wood like that. It's only a little bit that's left. And so tracking that energy and trying to figure out where all that energy went can oftentimes be extremely difficult. Keep track of energies. And so we're going to introduce a concept called momentum now. And when you have, in particular, collisions, it turns out momentum is extremely useful and real easy to track where things went. Another example would be like a car crash. You got two cars and they have a head-on collision. And now there they are, they're stopped. Where did all the energies go? It's hard to keep track of all the energies. You know, some energy went to bending the frame here, to twisting it there, heating some up here. The energy's all over the place. Tracking that, almost impossible. Tracking the momentum, we're going to see, extremely simple.
Sound also counts as part of that, right?
Huh?
Sound.
Yes, sound is part of it. all the side effects that happen, a little bit of energy goes into all those things, but sound in that case would be a rounding error. Could be a nothing burger, but yes, some energy does go into sound. Okay, so momentum is going to be extremely useful for doing these types of calculations, much easier than trying to track the energies or to use Newton's laws and try to keep track of all the forces themselves. That's a nightmare. Momentum, much better. So what exactly is the definition of momentum? Momentum, it's a vector quantity. It's just a mass times a velocity.
Is that a P?
The P.
Is it P for momentum?
Because momentum. M was taken for mass, I don't know.
Oh.
However it comes out.
Okay, mass times your velocity.
I don't know if it's somehow a consequence of what Newton called it, because he didn't call it momentum. He called it, I can't remember what he called it. He had his own name for it though, so maybe it's a fault of that. I have no clue where the P comes from. So momentum is just mass times velocity. Now the closest thing that we've had kind of behaving like momentum so far is force. What is force?
Your mass times your acceleration.
Mass times your acceleration. So rather than mass times acceleration, it's just mass times velocity.
So do you get momentum when you integrate your force?
You can. That is a way to get momentum. So exactly like what you were saying, notice what's acceleration?
It's the derivative of
It's the derivative of velocity with respect to time. So if I rewrite my force, I write my force as mass times acceleration. Now, if m's a constant, you can just move it inside. And so it's actually the derivative with respect to time of mass times velocity. Or in other words, F is equal to the derivative with respect to time of your momentum. And this is actually the way Newton formulated his second law. He said that the total force will always be, sorry, that's a force vector. Your net force will always be equal to the change of the momentum of the system. And that's the way he wrote it. We typically now write it as F equals ma, but that's not the way he formulated it.
Makes sense.
It's the time derivative of your momentum. So yeah, reformulating Newton's second law, there it is, where this is the sum of all the forces acting on whatever the object is, and that's the momentum of the object. What are the units of momentum? Well, you can see right here that the units of momentum are kilogram meters per second.
Yeah.
So kilogram meters per second. Now, if I multiply top and bottom by seconds, I get kilogram meters per second squared times seconds again. You see that? And kilogram meters per second squared is what we mean by newtons.
We can do it second.
So you can call it Newton seconds, or you can call it kilogram meters per second. We don't have our own special unit for momentum.
Which makes sense, I guess.
So you'll see it come up both ways. Sometimes you want to think about it as, turns out sometimes you can think about it as a force times a time, gives you a momentum.
Okay.
Which you can see from up here, a force gives you a change in momentum with respect to time. If I take a force and I multiply it by some amount of time, I should then get a change in momentum.
Right.
The same way that if I take an acceleration and I apply it for some amount of time, I get a change in velocity. If I have a force and I apply it for some amount of time, I get a change in momentum.
Which makes sense because you get momentum times velocity compared to force times is mass times acceleration.
Yeah, that makes sense.
Right, they're just scalar scalings of each other is one way that you can initially think about it.
Oh, that's cool. Quick.
Okay. So anyways, so that's one way we'll think about it. We'll sometimes calculate momentum by taking a mass and multiplying it by speed. Other times we'll calculate momentum by taking a force and multiplying it by time.
And intuitively, what does momentum encode? Like, what information do we get from momentum?
The momentum, it's. I wish I remember what David called it. He called it like the motion quantity or something like
quantity
that.
of motion is
Quantity of motion or something like that. Because somehow a heavier object moving with a velocity has a bigger quantity of motion than half that same object moving with the same velocity. So our intuition for velocities are very close to our intuitions for momentums and the way they behave. It's just like now we're taking into account the mass there.
Okay.
And the P comes from some random Latin word like impetus or something.
Probably, I believe it. Because when he initially published, even though he was English speaking, at the time it was still the norm that you publish intellectual works in Latin. So it's why it's always called his Principia instead of his principles.
Makes sense.
Anyways, so there we go. Now looking at this, if force is equal to the derivative, if the derivative with momentum with respect to time gives you a force, then if I integrate a momentum, what do I get? Or sorry, if I integrate a force, what do I get?
You get the momentum.
You should get a change in momentum, right?
Yeah.
So if I do from, oh, I actually have it written out right here. So just looking at this, so if I take some force now, and I integrate that force from time 1 to time 2, then what is that the same as? Well, since a force is just a derivative of momentum with respect to time, and I'm integrating that with respect to time, this goes back to our fundamental theorem of calculus. The derivative of something integrated just gives you back that thing evaluated at the two endpoints.
Oh, that's kind of
So if I take the integral of the change in momentum with respect to time, I'm integrating that with respect to time, then it just gives me our initial function, your momentum, evaluated at the two endpoints, which is how we typically solve all our integrals.
So if you want to find your momentum, you just integrate your force.
Well, kind of. So notice what that gives you. It gives you your momentum at those two times.
Yeah.
Or it gives you a change in momentum. A final minus an initial. So it's almost correct to say that integrating the force with respect to time gives you a momentum. What it really gives you is a change in momentum.
Gotcha. Okay.
So a momentum at some endpoint minus a momentum at some start point, the change in momentum. This comes up so often, we have a special letter that we use for it, J.
Is that a vector?
Yes, it's a vector quantity because this is the difference of two vectors.
Oh.
So if, just draw it out pictorially for a second, think that's what we're seeing. If this is P1, and this is P2, so your momentum was like this, and I apply a force for some time, now your momentum's like this, then your change in momentum is like that.
Yeah.
Here's your delta P. And so your change in momentum is going to be in the same direction as your average force vector.
Right.
Okay. So anyways, that happens so frequently, we have our own special name for it, and we call it J for impulse.
Impulse.
Of course.
I've heard that before.
J for impulse. So that's your impulse. An impulse is just a change in momentum. And we often think about the impulse as it's going to be a vector quantity, so it's the difference of those two things. And the impulse is always going to be in the same direction as your average force was.
I'm going to assume it has something to do with jerk, which is why it's a jet.
No. Maybe. I mean, there is a jerk that goes on as your acceleration changes. Oh, no, there doesn't have to be. There could be a constant acceleration the entire time. So, don't think jerk comes into the picture in any way. But, the last connection I wanted to make is, here's its precise definition. If we think about now the average change, remember how you do the average of an integral? You just divide it by the width if you want the average height, going back to calculus. If I want the average height of some integral, I take the area, which is what the integral gives me, and I divide it by the width.
Yeah.
And that gives me the average. So, probably should have scribbled this out somewhere. So right here now, if I look at my average force, average height, average force, same thing. The force is a height if we were graphing it. Then my average force, average, that was awful. Average is going to be equal to this integral, which is jerk, impulse, now you got it in my head, over T2 minus T1, our base, or delta T.
Wow, yeah.
Or in other words, another way that you can calculate your impulse, if you know your average force, maybe you don't know the force at every instant of time, but you know the average force, then it's just going to be equal to your average force times delta T. Which, once again, these newtons kind of scream out at you. These units scream out at you, not these newtons.
Yeah.
So a force applied over some amount of time gives you a change in momentum. It gives you an impulse.
And that's used a lot in like rocketry.
We'll get to rockets here in a second. Well, no, it'll be the last thing we talk about, but we'll get to rockets today.
Sick.
Okay. So there we go. That's most the deep theory for today. Any questions about that? Introducing the new definitions that we're going to be working with.
Going back to like the block example, how does this concept of momentum help us understand that?
Okay, so then that's going to come from the next part, which is going to be conservation of momentum.
Okay.
So we'll go over that, and then we'll start talking about the crazy consequences of this and how simple it makes everything. So that T was not part of this, so over there. Okay, so now we're going to derive what is called the conservation of momentum from this definition of momentum. So imagine that we have some ridiculously complicated system.
Okay.
It has all these different masses, and different masses spread out however they're all spread out. And maybe these are just a bunch of electrons and protons. Maybe it's a dust cloud out in outer space and they're all exerting gravitational forces on each other. But the point is we have all these particles and they're all interacting with each other.
Right.
All somehow exerting forces on each other. You with me?
Mm-hmm.
And so, what we're going to be interested in is talking about the total momentum of the system.
Right.
With me? So what is the total momentum of the system? It's going to be the momentum of particle 1, plus the momentum of particle 2, plus the momentum of particle 3, right? And our goal is to try and come up with some way of talking about this total momentum. That's our goal. Now, our first observation is how is momentum related to force?
That's
Integral. Oh. Yeah, or derivative of.
Whichever way you think about it, right? So if we take the derivative of momentum, then we get the forces. So what is the derivative of my total momentum then?
is your forces added together.
It's going to be the total of all the forces on object 1 will give me my change in momentum 1,
Yeah.
plus the total of all my forces on object 2, plus da-da-da-da-da. Good so far?
Yes.
Now let's look at one of these things. What is my total force on object 1? So we're going to write that out right here.
Is the sum of your vectors.
I have to check what is the force on 1 by 2. So 1 could be exerting, if this is like a proton and that's like a proton, it might be exerting a force that way pushing on it.
Yeah.
So it could be feeling a force this way, F from 2. Mm-hmm. It might be being pulled towards object 3, that would be F1 on 3. Sorry, can you see those subscripts at all?
Yeah.
Yeah, okay.
1 comma 3. And then there's going to be a force on it for 4, 5, 6. There's going to be n forces on this thing from all the n particles in this stupid complex system.
Mm-hmm.
And then on top of that, there could be some external force being acted on it. That's not part of our system. So maybe just gravity also somehow from some nearby star. So we're talking about some gas cloud of charged particles in outer space with a sun nearby or a star nearby exerting some external force, whatever. So the sum of all those m forces plus F1's, what I use for external?
Yes.
EXT. EXT. Sorry, that's kind of a mess. And that would be for 1. So F1 total is going to be all that.
Mm-hmm.
Now we got to do that for the second particle. And so we're going to have on our second particle, let's erase this external one. We know that the external one's there. But now for particle 2, what does it have? It has, first off, the force on it from 1. So we're going to have the force on this thing, and this is going to be the force on 2 from 1. And how does the force on 1 from 2 compare to the force on 2 from 1?
Newton's third law, isn't it?
Newton's third law, and so they're the same, but
In opposite directions.
in opposite directions. You see that?
Yeah.
And so when I am doing this sum right here,
Oh, okay.
one of my terms is going to be this, one of my terms is going to be this.
They cancel out.
And they're going to cancel each other out. And F13 is going to be canceled out by F31. And F23 is going to be canceled out by F32. And all of your internal forces are all going to perfectly cancel out. This is why it's so amazing.
What does that mean? Like,
And so what that means is your change in momentum is really just equal to the external forces on 1, plus the external forces on 2, plus the external forces on n. And all those internal forces, however crazy, however compact, or however complicated, they have no effect on the momentum of the system as a whole. In other words, if I were to grab a piece of TNT and throw it in outer space, it has its momentum. If you came along and you lit the TNT and blew it up, and we kept track of every single atom and added up all the momentum, it's the exact same as it was before. And that massive explosion going off, all those crazy internal forces, doesn't change the momentum. And so this is why it's so much easier to track the momentums
Rather than force.
rather than the forces or the energies created by the forces.
Right.
Right? A lot of energy going on. TNT stick going along. What's the kinetic energy? Almost nothing. Blow it up and now those atoms are shooting out. There's tons of kinetic energy all over the place. And how on earth to talk about that? I don't even know where to begin. But the momentum, that's simple.
Yeah.
Didn't change. So, the change in your total momentum is equal to the sum of the external forces. The change in your total momentum is equal to the sum of your external forces. You with me? And so if the sum of your external forces is 0, then what do you get when you integrate 0?
But you
So a constant.
Just a constant.
yeah.
Oops. If the derivative is 0, then the momentum
It's constant.
is a constant. Sorry. That was probably confusing.
Right, because. Right.
So, those are saying the same thing. The sum of the external forces being 0 is the same thing as the change in the momentum being 0. And if the momentum's not changing, then it must just be some constant value.
Yeah.
Make sense?
Mm-hmm.
Wrote the exact same thing there. The momentum is a constant. So, in general, if the forces are 0, then the momentum is a constant.
Which makes. Yeah.
And that's the conservation of momentum. And now that's why it's so much easier in all these examples to talk about it. I can easily calculate, if we talk about shooting a block of wood, if I know the mass and the velocity of the bullet, that tells me the momentum. And so the mass and velocity of the bullet together with the block of wood after the bullet goes in has to be the same. The momentum has to be conserved.
But you don't have as much kinetic energy.
No, you lost a ton of kinetic energy, and that went into the deformation of the block and the heat and everything that happened. But the momentum is still the same.
Yeah.
Good? Alright, so that's the crazy conservation of momentum. The fact that Newton's third law works the way that it does. Okay, one thing I want to stress very heavily. A change in the kinetic energy and a change in the momentum are very, 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 very different things. Now, it's easy to get confused by these things because how do we typically get our change in kinetic energy? Notice that that's integrating a force. A force's dot product with a displacement. How are we getting our changes in potential energies? That is a force times a dt. When you integrate a force times a scalar, the result of this is a vector, sorry. You hear what I was saying. When you take a vector times dt and you integrate this result is a vector.
Yeah.
Up here, when you take the dot product of two vectors,
It's
it's
a scalar.
a scalar. And now we're integrating a scalar and we get a scalar.
Yeah.
Energy is a scalar quantity. Momentum is a vector quantity.
Which makes sense.
These we typically get by integrating a force with a displacement. These we typically get by integrating a force with a time. So they're closely related, but very different at the same time.
Do we have any way of figuring out the change in momentum with the change in kinetic energy?
You can, yes. Because if you know the change in kinetic energy, then you're able to determine the changes in the velocities, most likely. And there you can get the changes in the momentums.
Oh.
So yeah, you'll use one, help calculate the other, that you'll do all the time. But, very different. And it will be not too uncommon mistake to accidentally go from one to the other of those. Because in general, look how closely related they are. How do we calculate our kinetic energy? 1/2 mv squared. How do we calculate our momentum? mv.
Yeah.
Now you notice that, well, do we want to say that? I'm not, okay, I'll say it once and then I won't stress it anymore. But notice that this is in some sense like an integral of that.
Yeah.
But now we won't stress that. Okay. So we said that. Let's go back to a problem that we did. It was one of our example problems. We had these two ice boats.
Yeah.
on some frozen lake or something like that. So these are their cells, that's the boat, and then they have the blades at the bottom. And they both slid across some distance, S, across some finish line. This one had a mass of M, this one had a mass of 2M. Good so far? The wind is blowing them on both of them with the exact same force, and there's no friction, so the wind's the only force on it. The question was, which one, so when this crosses this line, it has a particular speed. When this one crosses this line, it has a particular speed. Oh wait, that wasn't the question. The question is, when this one crosses this line, it had a particular kinetic energy. When this one crossed this line, it had a particular kinetic energy. Which one had more energy when it crossed this line?
First.
The latter one, I assume, right?
And the answer was, they had the exact same kinetic energy when they crossed the finish line, because the same force times the same distance does the same amount of work.
Oh, just cross the finish line.
Just to cross the finish line.
Yeah.
Now, which one crosses the finish line first?
It's the latter one.
This one crosses the finish line first. But by the time this one crosses the finish line,
It has the same energy.
it will have had the same amount of work done on it, so it will have the same kinetic energy as this one had when it crossed the finish line.
Right.
But now if we look at them both for some period of time, then this one is going to have had, well, now how do I want to say this? Let's just re-ask the question this way now. Now, when they reach the finish line here, which one of them has more momentum?
When they both reach the finish line?
So when this one reaches the finish line, measure its momentum. When this one reaches the finish line, measure its momentum.
The second one, so the 2M would have more momentum.
This one has more momentum than this one has by the time it crosses the finish line.
So it's heavier.
And intuitively, how does that make sense? It's going to go slower.
They'll have more force behind it.
And so the force is going to be being applied for a longer period of time. Force times distance gives you kinetic energy. Force times time gives you momentum. So same kinetic energy when they reach the finish line. This one will have less momentum when it reaches the finish line because it will reach it quicker.
Right.
Okay. So, difference between kinetic energy and potential energy. A force applied to two objects for the same distance means same kinetic energy. A force applied to two objects for the same time means the same momentum.
I thought we decided the second one had more momentum.
Second one had more momentum because it takes it longer to reach the finish line. Because by the time it reaches the finish line, this one has already reached somewhere over here.
But at the same time, it's the same momentum.
Same time would be the same momentum. So the momentum this has by the time it reaches here is the same as the momentum that this has by the time it reaches here.
Okay.
But if we just had to go from here to here and then measure its momentum, this one will have less than this one. So they'd have the same kinetic energy, different momentums. Those are not the same values. Those don't measure the same things. They're closely related because one you think about we multiply by time, another one displacement, and it's easy to confuse those two things. Okay. Now, momentum, I told you, one of the things it's most useful for is just talking about collisions. And so we're going to talk about three types of collisions. Let me move the camera so that we can maybe get all three of those and have everything about collisions in one go. Yes. Okay. So, three types of collisions that we're going to have. We're going to have completely inelastic collisions. We're going to have completely elastic collisions, sometimes just called elastic collisions. I think that's what the author actually calls it. But you'll hear it both ways. And then we're going to have what are just called inelastic collisions.
So what, if you're playing billiards, what determines if it's gonna hit the ball and stay there versus if it will go with it?
So billiards is an example of elastic collisions. And so we'll have a lot to say about elastic collisions. Let me give you an intuition for each of these. So let's start with the billiard ball and see what's happening there. In a billiard ball collision, well, now it's easier to start with the completely inelastic collision. So let's start with this one. Completely inelastic collision. Elastic somehow means it bounced off, right? Somehow bounces. So a completely unbouncing collision means that they perfectly stick together. This would be like a collision between two balls of glue. They're going to stick together.
Okay.
Or you got two bumpers and you got some Velcro attached to each end, and they go and they stick together.
Okay.
Or two cars. You have a collision, head-on collision, two cars cram into each other, and then they stick together. It's one ball of mess.
They don't bounce back.
They don't bounce back. So what causes them to not bounce back? Typically what that means is that there was some sort of deformation in the object.
Right.
So when two cars crash, that's a lot of deformation.
Mm-hmm.
Let's look at the counterexample where they completely bounce back. In billiard balls. So in billiards, when two balls collide with each other, what happens? When they hit, this one dents in a teeny bit, that one dents in a teeny bit, and then bounces back out.
Yeah.
Right? And it reassumes the shape it had prior to the collision. And so there is no deformation. It kind of bounces right back out, and it has the same shape that it had prior to it. And so that's a completely inelastic collision.
Yeah, but sometimes when you hit it, then it will just take the place of the other ball, stop moving the other ball.
We'll see that exact scenario. But the point is, they in no way stick together.
Yeah.
And there's no deformation going on. Keep in mind that the energy has to go somewhere when there's a collision. When two cars collide and we have a completely inelastic collision, where'd all the energy go? Into deforming the cars and creating all sorts of heat everywhere. When the billiard balls go and collide, where'd the energy go?
It's movement.
It pretty much all had to go into kinetic energy.
Yeah.
There wasn't really any heat. I mean, there's a teeny bit of heat, and there was the sound waves, but those are all negligible compared to the kinetic energy of the billiard balls.
Right.
And so there was no deformation, and so all the energy is still in kinetic energy. Or another example you'll see on some of your problems is you'll think about two bumpers or two blocks of wood with springs on the front. And they'll go and they'll bump into each other, the springs will coil out and then compress back out and pop them back out. And all the energy will ultimately go back into kinetic energy. It's kind of what's happening there. You can kind of think it's bending in the ball. It's like it's compressing on a really strong spring on those billiard balls.
Is that what
And then
actually
pushing back
happens?
out. Huh?
Is that what actually happens?
Yeah, it's denting in and popping back out.
What if you have a completely?
Wouldn't that break it?
No.
What if you have a completely uncompressible sphere? Like, would it still move if you hit it?
If you had a completely uncompressible object, then you've got, I don't know, because that's just not reality. Everything gives some. You would have to have like instantaneous forces applying. You would be talking about like an infinite acceleration
But would
or
it
an
still,
infinite jerk.
would it still move?
The closer you get, there's always going to be some. So the answer will be yes.
Is it bouncing because of the deformation? That doesn't feel. Feels like it should move, regardless of how it forms.
Intuitively, it's like a really strong spring. Right? And so you can think about zero compression is like a spring constant K of infinity.
Oh.
That's one way to think about it.
Interesting.
Okay. But yeah, there's going to be slight boop and pop back out. Anyways, so energy has to go somewhere. If the energy can't go into any sort of deformation, then it pretty much all has to stay in kinetic energy. So in completely elastic collisions, or what your book's just going to call elastic collisions, then kinetic energy is going to be conserved, and you're not going to lose any kinetic energy in the collision. In inelastic collisions means that there's some deformation, some sticking, some something. Then energy is not going to be conserved. And in completely inelastic collisions, that means that the objects actually stick together at the end.
Okay.
So completely inelastic, they stick together. Inelastic, there was some deformation, maybe a little bit of sticking, but they didn't completely stick together.
Which is where all cases would fall.
Which is, in reality, what everything is. And then there is elastic or completely elastic, those are synonymous, where it completely bounces back. It's a completely elastic material.
Okay.
Good? Okay. So now we're going to do a deeper dive, particularly into completely inelastic and completely elastic collisions. Momentum is going to be conserved in both these cases, because no matter what the collision is, there are no external forces. When two cars crash, there's some friction on the road, but that is completely negligible compared to the forces of two cars ramming into each other.
Yeah.
What's a conservative force?
A conservative force, that would be like gravity, that would be like a spring. It's a force where you can somehow get the energy back out.
Oh,
I
yeah.
fight gravity, putting energy into the system, and now I can use gravity to get it back out.
Okay, that's what I thought. It was just,
So that's another way to think about it is elastic collisions, those are like conservative collisions. Because you can think about it as basically compressing a spring.
And you get the energy back out.
And you get the energy back out. These ones, no.
You kind of lose your energy.
You lose your energy to the deformation.
Okay.
yeah.
Okay. So with that intuition, let's do a deeper dive and actually start looking at some of the math. So, setting up a scenario, we'll keep it one-dimensional for now, just for the sake of simplicity. But all the math here works in a two-dimensional case.
Right.
Okay. So I've got some object with mass little a, I've got some object with mass little b. However they're moving, they're on some sort of collision course. We're going to do a completely inelastic collision, so we'll think about them as like having Velcro. So this has all the hooks on this side, and then this has all the strings that the hooks catch onto on that side. So Velcro, right? And they're going to have some collision, and after the collision, they're going to perfectly stick together with some new velocity. So V1A is the velocity that object A has in the beginning. VB1, the initial velocity of V, and then V2 is just going to be their ending velocity.
On frictionless surface is what we're.
On a completely frictionless surface. Good. They're floating out in space somewhere on a collision course, and they stick together after the collision.
Perfectly aligned.
Maybe perfectly aligned. My picture's showing it that way, but on some collision course.
Yeah.
Maybe they're going like this and sticking and going off,
Oh.
and all this still works the exact same.
Yeah.
Good?
Yep.
All right. So, since there's no external forces acting on it, no friction, so no external forces acting on it, the momentum has to be conserved. So the momentum before the collision has to be equal to the momentum after the collision.
Isn't momentum conserved
What?
even if there is extra forces?
No,
Oh.
because the change in momentum is equal to whatever the external forces are. So if there's an external force, that changes the momentum. If there's, think about it the way we were thinking about before, if there's an acceleration, there's a change in velocity. If there's a force, an external force, then there's a change in momentum.
Okay.
So you're saying it's conservative. How is that? When two cars crash, it's not a conservative force, is it?
No, nothing to do with conservative forces. If the external forces are zero, conservative or not.
Then the momentum.
In other words, when you're talking about two cars crashing into each other, what are the forces that those cars are exerting on each other? Extremely massive compared to friction. Friction's nothing.
Yeah.
So you have the weight of the cars pulling them down, and the normal force pushing them up, so those cancel out.
Yeah.
Friction's basically zero. And so the total external forces occurring in a car crash are essentially zero.
Okay.
And so the momentum is essentially conserved.
Right.
Doesn't conserve mean, loss to deformation also counts as conserved?
For momentum.
That's energy being lost. Momentum can't be lost due to deformation. That's what we're finding out here. Internal interactions don't cost you any momentum.
Oh, that's what that was. Oh,
That's what all this was. It's only the external ones. So two cars crashing into each other. There's a lot of internal things going on. It's nuts. It's crazy complicated. But now look at the car crash as a whole. And what are the forces acting on the car crash?
One or either.
Gravity pulling it down, the normal force pushing it up, they perfectly cancel out each other. The net force on the car crash is zero. The internal forces on the car in the car crash are nuts.
But it kind of feels like after the crash is done, there's no momentum anymore.
Now, so we're talking about the instant after the cars are done crashing. Because what really happens, the cars crash together, and now they're in some weird shape sliding across the cement, and then friction matters a lot. So we're talking about, you got the car crash, and the instant after the car crash, there's still all that momentum.
But what about they hit each other perfectly head on and like same speed, same weight, they hit and stop.
Oh, perfect. So let's say I've got a car coming this way and a car coming this way, both weighing 1,000 kilograms, both moving at 10 meters per second. What's the momentum of this car? 10 meters per second times 1,000 kilograms gives us 10,000 Newton seconds. This one has 10,000 kilogram Newton seconds this way.
Yeah.
They're vector quantities. What's this vector plus this vector?
You know?
Zero. And so in a head-on collision, it better come out 0.
I see.
It doesn't though, in reality.
It does, if it's completely head-on.
Yeah.
Now, if they're on a little bit of an angle,
You'll be happy.
then they'll shoot off that way.
And then the first.
But it will be the vector sum of the two momentums.
So,
Yeah,
okay.
but they usually shift one way or the other.
This is literally part of what happens when even examining a crime scene, trying to figure out what exactly was happening in a collision.
Yeah.
And one of the things they look at is how the result of the car crash goes after the fact. And it can help them re-figure out how the collision must have occurred.
Yeah. Okay.
Okay, so here we are, back to the scenario. So here's the momentum of this object, mass times its velocity. Here's the momentum of this object. Here's the momentum of this object. The momentum we had before the collision has to be equal to the momentum we have after the collision. So the sum of those two momentums has to equal that momentum.
Okay.
So this will be what a bunch of your problems early on are like. They'll say these two objects collide. They'll give you the masses and the initial velocities. Standard problem will be now find the velocity they have after the fact.
So just add the masses and then divide it out.
Yeah, so typically you're going to be solving for the V2 here. So just divide by MA plus MB and here it is.
Oh,
Now you're
I
typically
didn't
going
see
to have this in 2 dimensions. So you're going to do this for the x direction and then again for the y direction. And then put them together to get the resultant vector.
Right, so you need to come up.
So it's the exact same math in both directions is the way you'll typically do it.
Got it. Okay.
Break it up into its x direction and its y direction. So
momentum in x and then momentum.
the momentum in the x direction is conserved, the momentum in the y direction is conserved. And so that will be in the x direction and then again in the y direction.
Right.
And it'll be the same math. Good so far?
Mm-hmm.
Okay, now let's not just say kinetic energy is lost and use our intuition to say kinetic energy is lost. Let's prove that kinetic energy is lost in these types of collisions. So, going to prove that kinetic energy is lost in a collision like this. Just to keep it simple, here's the case we're going to look at. I'm going to say object A collides into object B. We're going to say that object B isn't moving. So we're going to pick our reference frame to be from as though we were sitting on object B.
Right.
Because that's, notice if it was moving with a velocity, it's an inertial reference frame, and us being on the block is also an inertial reference frame. So you can always do it from that block's perspective if you want, and it shouldn't change anything.
Yeah.
It's just going to help our math be a little bit simpler.
Right.
Good? Okay. So you can think about that as 0, or we're looking at from that object's reference frame. Comes out the same way both ways. It's just going to clean up one of our terms.
Yeah.
And let's prove that kinetic energy is lost in this collision. So it's going to hit that object, and they're going to stick together. Kinetic energy is going to be lost. Let's prove it. What is the kinetic energy at the start? Well, this object isn't moving,
So I don't know.
so it's just going to be the kinetic energy of this object, which is 1/2 its mass times its velocity squared. What's the kinetic energy at the end? It's going to be 1/2 the mass of that object times its velocity squared.
Yeah.
With me so far? So there's our two kinetic energies. Now we know that momentum is conserved since there's no net force. So let's look at our momentum equations. I know that the momentum at the start has to equal the momentum at the end. Here's the momentum at the start.
Okay.
And the momentum at the end is just that times that. You with me? Solve for V2. Exactly what we did right here. But this time, one of the velocities is 0.
Okay.
Good so far? Okay. Now, what I'm going to be interested in is K2 compared to K1. If kinetic energy is at loss, then K2 over K1 should equal 1.
Right.
If K2 is smaller than K1, if we lost kinetic energy, then this ratio will be less than 1.
Yes.
And if we somehow gain kinetic energy, which would be the strangest of all, then this will somehow be greater than 1.
Is that possible?
Now, well, I don't know. Probably. If we stopped and thought about it, we could probably come up with a way to make that happen. Like have them go and collide, but that one's also got some explosive material on it. Okay. Anyways, so here's the ratio that we're going to be looking at. So let's, really quick, what is K2? So I know what K1 is. That's right here. What is K2 now? But I'm going to rewrite velocity 2 in terms of V1.
Okay.
So I know what V2 is in terms of V1. There it is. So I'm going to rewrite this V2 in terms of V1. And then that way I'll be able to take the ratio. So kinetic energy afterwards is equal to 1/2 m and then V2 squared. Here's V2. Here's V2 squared. That's a square right there.
Yep.
Good so far? And then, notice, MA plus MB squared, cancel one of those out with one of those. We get 1/2 MA squared times V1 squared over MA plus MB.
Yep.
So now, we're just looking at the ratio of this to this. Your ending kinetic energy to your starting kinetic energy. So I'm going to look at this quantity divided by this quantity.
Okay.
Now, dividing by K1 is the same thing as multiplying by its reciprocal. So I'm just going to look at the reciprocal of this. What's the reciprocal of this? 2 over MA times V1 squared.
Yep.
So here's K2. Here's 1 over K1. I'm going to just multiply.
That'll just cancel out.
Right. So the 2 cancels out with the 2. MA cancels out with one of the MAs. V1 squared cancels out with the V1 squared. And so we were left with one of the MAs and the MA plus MB. And notice that this has to be
Less than 1.
less than 1.
But why?
Ah,
Oh, obviously.
yeah. 5 over 5 plus x always has to be less than 1 if x is a positive number.
And we can't have like a zero mass in this situation.
Well, let's think about it. Let's think through what that means. What would happen if this mass was basically 0? Say that this was a bowling ball in outer space, and this was a ping pong ball in outer space with glue on it, so it's going to stick to the bowling ball. What happens? The bowling ball just keeps on moving the way it was moving, and this pretty much does nothing. And so that's what this is saying, is hardly even changed anything.
Yeah. Makes sense. So you lost kinetic energy.
So you lose kinetic energy.
That's interesting.
Now, think about what happens if the kinetic energy lost, if I take a ping pong ball made out of glue, and I throw it against the wall, and it sticks to the wall.
You lost all of it.
All the kinetic energy is gone, which is what this says. If your MA is essentially 0 compared to your MB, then it's essentially 0 kinetic energy.
Is it actually 0 kinetic energy?
Well, no, because you did whack some atoms and they jiggled more and blah, blah, blah. I mean, the energy gets absorbed and you can now call it internal energy or whatever. It's essentially 0.
Okay.
Okay, so there we go. Kinetic energy is in fact lost in those types of collisions. And this gives you a sense for how it's lost. Okay. So that was completely inelastic collisions where they stick together. Did I want to say anything more about looking at the equations before we go on to elastic collisions? I think we're okay with it. Okay, so let's move on now to completely elastic collisions, where they completely bounce back. So in inelastic collisions, momentum was conserved. In elastic collisions, both momentum and kinetic energy are going to be conserved.
Okay.
Okay, so now we're going to have two sets of equations that we're going to be able to use over and over again. The kinetic energy at the start has to equal the kinetic energy at the end. The momentum at the start has to equal the momentum at the end. So setting up a picture, well, this will be specific to that. I didn't just draw one out, but if we have these two blocks moving towards each other, and they collide, and then they bounce apart, then what would be the kinetic, let's just say, I'll erase this here in a second, but let's say that this is moving this way with B1. Okay. So notice, two objects, they're moving, they collide, now they're bouncing apart however they're bouncing apart. Completely elastic collision, like billiard balls.
Yeah.
Okay, what is the kinetic energy of the system in the beginning? It's just 1/2 ma squared times its velocity squared.
Yeah.
Similarly, plus whatever the kinetic energy of this object was.
Mhm.
And that has to be equal to the kinetic energy of this object in the end, plus the kinetic energy of this object in the end. Notice that these are energies, so those are all scalar quantities. We don't have to keep track of any vector map there. That's dealing with energies.
Okay.
For this one, the momentum of this object plus the momentum of this object has to be equal to the momentum over here plus the momentum over here.
Okay.
And so you'll oftentimes be given two equations with two unknowns to solve for in your homework problems. And these will be your two equations.
Right.
Good? Now, let's do an analysis once again of a completely elastic collision. Completely elastic collision. Now, I'm going to do it in the scenario where this object is holding still, and this one just comes and bounces off of it, and then it starts moving. We'll do it from this object's reference frame. It doesn't change anything to do it from its reference frame. It just helps clean up the mass some. So it's one less quantity to keep track of.
Mhm.
With me?
Yeah.
Okay. So, this initially has some velocity that way of VA1. They collide, and now they're bouncing apart. That's what happens. Since the kinetic energy at the start and the kinetic energy at the end have to be equal, what's the kinetic energy at the start? It's just however fast that thing's moving.
Mm-hmm.
And what's the kinetic energy at the end? It's that one's kinetic energy plus that one's kinetic energy. Since the momentums are conserved, the momentum at the start equals the momentum at the end, then the momentum of that object equals the momentum of that one plus the momentum of that one. Good so far?
Mhm.
Now, what we are going to do is we are going to pretend that we're in a scenario where we know the starting masses and we know the velocity of this one coming at this one. Our job is to figure out the velocities after the collision. How do these things bounce apart? That's what we're going to try and solve for. So we're given two equations with two unknowns that we're trying to solve for. Here's in general what you're going to be required to do on your homework a bunch of times. So set up both my equations, this one, and now we're going to start solving. Alright, so let's get into solving. So, starting with our energy equation, so bringing down our energy equation, I'm just solving for this term because I'm trying to get VB2 by itself.
Okay.
So, solving for this equation, first off, multiply everything by 2, gets rid of all my halves. And since I'm solving for this, I'm going to move this one to the other side. So MB VB2 squared is equal to that one minus that one. With me so far?
Okay.
Going from here to here, just factor out the mass of object A.
Mhm.
Now, hopefully you are familiar with this algebra, but A squared minus B squared is the exact same thing as A plus B times A minus B.
Yeah.
Okay, so that's all I'm doing here is splitting that up into two factors.
Okay.
So this is equal to that. Good? Now that was using my energy equation. Got it down to there so far. Now come use my momentum equation. Once again, solve for the one that has VB2 in it. All I'm doing is moving this one to the other side and then factoring out the MA. So I have MB VB2 squared equals this, and I have MB VB2 equals this. I'm going to now take this divided by this is equal to this divided by this. Since this is equal to this, and this is equal to this, that divided by that is going to be equal to that divided by that.
Yes.
I'm re-scribbling that up right here.
Okay. And that cancels out.
So you see, right, it's just a nice way of canceling out because we were just looking for the VB2 so far. So let's see, the MB cancels out, the VB cancels out with the VB, just leaving one VB. The MA cancels out with the MA, the VA1 minus VA2 cancels out with the VA1 minus VA2, leaving the VA1 plus VA2. So we get this great equation right there.
Your final velocity is the sum of your two initial velocities? Is that what it's saying?
No, that's a final velocity.
Oh. Okay.
Good so far? Okay. So now I have VB2 in terms of VA2. And now I can substitute that into one of my equations. I think I want to use this one. So since MB, this bottom equation, you see how that's the bottom equation, the one we got for momentum?
Yeah.
Okay. Then, doing my substitution now, I'm just replacing VB2 with VA1, VA2. Because now I'm going to solve for VA2. I got VB2 in terms of VA2, do that substitution to get VA2, and then go back to get VB2. Just like you do when you solve a system of equations.
Yeah.
Okay, so all I did is take this and substitute in that VB2. Follow me?
Yep.
Okay, now just multiply it through. So multiply that through to see what cancels. So MBVA1 plus MBVA2 is equal to MAVA1 minus MAVA2. All I did was multiply it out. Because now I want to get all my terms with VA2 on the same side. That's what I'm solving for.
Yeah.
So I'm going to move this one over here and factor out the VA2. I'm going to move this one over there and factor out the VA1. Good? Now finally, I got the VA2 by itself, so now just divide both sides by MA plus MB. And there we go. Here's VA2. Remember what we assumed you knew. We assumed at the start you knew the mass of the two objects and how fast the first object was flying at the second object. So here's how fast this object bounces away. And now we need to find how fast this object bounces away. So now we have VA2. Once again, come back up and look at this equation. So since we have this equation, then substituting in, I'm replacing the VA2 with this. Because now I need to get VB2 in terms of our known quantities.
Right.
Okay, so this VA1, I multiply it top and bottom by 1, or I multiplied it by 1, so I could have a common denominator with what this one's going to be. So VA1 is right here, VA1, and I just multiplied it by 1. Same thing top and bottom. You with me? So that, right there, didn't change anything. I substituted VA2 with what we know it is now.
Okay.
I multiplied this top and bottom by MA plus MB, simply because I knew that this one was over MA plus MB, so that they have a common denominator. So that's why I multiplied that top and bottom by that. Okay, so now going from here to here, factor out the VA1, there it is. And now, if two fractions have the same denominator, you can just add them together. What is 3/7 plus 9/7 equal to? 12/7. So since this fraction has the same denominator as this fraction, we can just add them together.
Yeah.
Okay. Now we have MA plus MB plus MA minus MB. What do we notice?
Well, it's there.
The MB cancels out with the MB, so how many MAs do we have?
2.
So we have 2 MAs. MA over MB down there, M times VA1.
And then you can't cancel out element.
No, that's it. So there's our equation. If you know the mass of the two objects and that initial velocity, then here are the final velocities of the two objects in terms of those known quantities.
If you know the what?
If you know the mass of the two objects and how fast the first object's flying at the second object, then you know how the velocities are after the fact.
What happens if your second object is moving initially?
So we'll have a little bit to say about that here in a second. But notice that so far it's like we were doing everything from this object's
Reference.
the reference frame that was moving at the same speed of this object. I don't want to say this object's reference frame because it's not the same as after the collision.
Right.
So it's like this one in your reference frame is moving that way towards the object, right? But I'm sitting here walking by as I see it, and so I'm moving the same fast as that object. And so now it's in my reference frame. So we chose a very special reference frame to help keep the math simpler.
Right.
how do we get out of that reference frame? So really quick, if we were to, should we use that one? Well, I'll say it once we're done. So let's stick with this for just a second, then we'll have that conversation. Okay, so here's how you get those two velocities, right? Now let's just do some sanity checks. What should happen if MA is much, much less than MB? That would be like I take a ping pong ball and I throw it against the wall, ignoring all air resistance.
It bounces off.
It should just basically bounce off at the exact same speed.
Yeah.
So, if MA is really, really small compared to MB, oh, sorry, over here. If MA is really, really small compared to MB, then we expect VA2 to basically be the same thing as VA1, just in the opposite direction. So let's check that. VA2, if MA is really, really small compared to MB, then that MA is basically 0. And that MA is basically 0. And so you get negative MB over MB, which is basically negative 1. And so VA2 is essentially negative VA1.
Oh, yeah.
Oh.
Which is exactly what we expected to happen. On the other hand, what happens if we're out in space and I've got some giant boulder that I throw and there's a dust particle in its way?
The dust particle.
Basically.
The giant boulder just keeps on moving,
Yeah.
right? And it didn't even affect it. So in that case, why do I keep going to that picture? In that case, we would expect, so we're talking about the case where MB now is way smaller than MA, right? So if MB is much, much smaller than MA, MB is basically a dust particle in the way of MA, then how does VA2 look after the collision?
Like VA1.
It looks like VA1. It just keeps moving that way. It definitely doesn't bounce back.
Yeah.
We drew it as bouncing back here just cause, but it can go all sorts of different ways depending on what the masses are. Right?
Yes.
And so we would expect VA1 to be the same as VA2.
Other way around.
No. If here's my velocity before, and you're a dust particle in my way, my velocity after the collision hasn't changed.
Right. So we expect VA2 to be the same as VA1.
Oh, sorry, I thought that's what I said. You're right.
Okay.
That's what I thought I said. Okay, so yes. So now let's look at what happens when MB is basically 0. MA minus 0 is MA. MA plus 0 is MA over MA 1. So VA2 is the exact same as VA1.
Sick.
Okay.
That makes sense.
All right. Now let's look at when they have the exact same masses. Now what do we expect to happen?
They now
And here's what Zach was saying with billiard balls. When you hit it perfectly on, you notice the one billiard ball stops and the other one starts going. Or if you played with, what are they called? Those balls where it whacks one and the other one pops off.
Newton's
Newton's cradle.
Yeah.
cradle. Yeah.
Then that is where they all have the exact same masses. And so we would expect in that case that one stops and the other takes over
Okay.
in a completely elastic collision.
You're saying in billiards that most often it's not the case that they'll stop and then have the other one keep going. You're saying that's because of a
In-
weight imbalance?
In one-dimensional collision, then one will hit it and the other one will just take over and the first ball will stop.
Intuitively, it kind of feels like they should both hit each other and bounce back, doesn't it? Why, if they had the same mass, why wouldn't they hit each other and both
It's
bounce
like
back?
it's just sending the momentum along.
That's not very intuitive though.
All right. Well, let's see if the non-intuitive result is what the math says should happen.
Okay.
So let's look at what happens when they're the same. So looking at our picture, not this picture. Keep going to that. This picture. Okay. Looking at this one, what we're saying is, what we've noticed happen in billiards is, you hit this thing, and it hits into that one.
And it stops.
VA2 becomes 0, and VB2 becomes the exact same as VA1.
Yeah.
So let's check that. So over here, what happens when the masses are the same? A number minus itself is
0.
0. And so VA2 is 0. Let's look at VB2. 2 times the mass, 2 times the same mass. If MA is equal to MB, this is 2MA, this is 2MA. And so it's 1. And so it's just equal to it. Good?
Mm-hmm.
Alright, so that's what the math says will happen. Now, what we were saying from before, looking for my eraser. Trying to remember the way your author writes this equation. I think he writes this equation, he rewrites it as VA1 is equal to VB2 minus VA2, but same exact equation. And now we did this, when we did this equation, we were doing it in the reference frame of I'm initially moving at the same speed as this object. So now let's quickly go from my reference frame now to your reference frame. So if my reference frame, so we did all the math in my reference frame, now in your reference frame what's going on? This object is moving over with instead VA1 prime. And this object is moving over with VB1 prime. We'll say yours are the prime coordinates, mine are just regular coordinates, right?
Right.
What is the difference between what you and I say about this velocity?
It's going to be smaller.
So if I say that object, let's set up a physical scenario. Let's say that in your reference frame, this one's going that way 5 meters per second, this one's going that way 5 meters per second. You with me?
Yes.
In my reference frame, since I'm moving along, this one's going 0, this one's going 10.
Yes.
In your reference frame, it was going 5 and 5.
Yes.
So how do we get my reference frame from your reference frame?
Divide it in half.
You need
Or
to just
value minus
add my velocity to everything,
Yes.
right?
Yes.
And so, if you want it now in general, you can just convert all the velocities, VA1 plus VB1 is equal to VB2 plus VB1 minus VA2 plus VB1. Now you'll notice you can cancel out this VB1 with one of these two VB1s, doesn't matter which one. You with me? And so we get,
Okay.
I'll just rewrite it up here. We have this extra VB1. So that one crossed out, this one crossed out. We have this extra one. I'm going to move it over here. And so VA1 minus VB1 is equal to VB2 minus VA2.
So, what is this saying geometrically?
Here's what it is saying. This is the relative velocities between the two objects. Notice that that's something you and I always agree on. I might say, right, let's go back to, in your reference frame, I'm going this way 5 meters per second. This one's coming this way 5 meters per second. You and I will disagree about the velocity of this object and the velocity of this object. What we always agree about is the difference in their velocities. We agree at how fast they're approaching each other.
Yeah.
That's what we always agree upon. And so that is what this is saying. How fast they're approaching each other is always equal to the negative of how fast they're approaching each other afterwards. So let me switch the signs and make it negative. It's always equal to the negative of VA2 minus VB2. Why the negative? Because they bounce and now separate from each other. So however quickly they're approaching each other before is how quickly they're moving away from each other after, is what that says. In our special case, that's what this says. So again, in our special case, let me move it around. We have VA1 is equal to, move this to the other side, then it's negative VB2 minus VA1. Moving that to the other side, this one, or sorry, moving that to the other side, oh, it should just be this. right? And so notice that this is, I want this one negative, so make that negative, put the negative there. Multiply both sides by negative, now put the 0 here.
Oh,
For VB. So that difference is equal to the negative of that difference.
right. Yeah, okay.
Oh, that's because I did VB minus VA up there and VA minus VB down here. Sorry. That's why signs will get on. But same concept. Doesn't matter which way you go. That's just going to change the signs.
Right.
Okay. So that's why it works that way. That's why you can just put back in the velocities. That's what that author was talking about when you read that part. It's kind of hard to follow him the first time you read that. Last concept we need to talk about now is center of mass.
Center of gravity, sort of.
Center of gravity, center of mass. No difference.
I like this one.
No.
No. Okay, let's set up a scenario. I've got a stick here. On this side, I've got 10 kilograms, and on this side, I've got 5 kilograms. Your job is to place a fulcrum so that these perfectly balance. So you need to place some fulcrum somewhere so that those perfectly balance with each other.
Are we taking into account the stick?
No, we'll ignore the stick compared to the weights. So this is an infinitely strong, infinitely thin piece of steel or whatever. With me?
Mm-hmm.
Where do you place the fulcrum so that you can balance those two things? If this is twice as heavy as that,
In between the half point and then the half point.
So quarter point?
Yeah, quarter point.
what you're going to need is this distance to be twice as long as this distance.
Yeah, which means you place it.
So it's at the
Oh,
1/3 one.
Third.
Okay, that makes sense.
Aw. Why is it third?
Why? Because if you have half as much weight, you need it twice as far to balance it.
That makes sense intuitively, I just don't know why.
No, right now we're just playing with intuition.
Yeah.
We'll come back to torques much later. This is just a good way to first get your intuition for the center of mass of something.
Okay.
So the center of mass of an object, one of the most intuitive ways to think about it, is it's the point that you have to balance. Because then, if that's like its center of mass, holding up right there is the exact same thing as holding up the whole object. It's as though all the mass were centered there.
Yes.
In other words, if I had you completely blindfolded, you would not be able to tell, and you're just holding out your finger, you would not be able to tell the difference between me having 15 kilograms spread out like that, balanced on your finger right there, versus you just holding up all 15 kilograms on your finger. It'd be as though all the weight were right there, at wherever you're holding up your finger at.
Okay, that it makes sense now.
Okay.
So let's really quick calculate center of mass. We'll stick in one dimension for a second.
Oh, I didn't think about that.
So we'll look for your x center of mass in one dimension. We'll set up some coordinate system. We'll say that you have 10 kilograms here, 10 kilograms, and then over here you have 2 kilograms. Oh, I put the kg underneath. This is at x position. We'll say, give me a number,
6.
6, and we'll put this one over here at
3.
18. I don't know, just making something up. Okay, where is the center of mass going to be on these two things?
Center of mass is going to be
1/5 along.
You're thinking that this one is 5 times bigger than that one. So wherever the center of mass is, this distance has to be 5 times bigger than that one.
So it's 1/6.
Alright.
So this has to be 1/6, whatever the distance is here.
Right.
And so what's the distance between the two?
6, 6.
12.
12. What's 1/6 of 12?
What? Do we need to get 12?
8 minus 6.
So what's 1/6 of 12?
2.
2. So it's going to be 2 units over. It's going to be over here at 8, would be your center of mass. And so your center of mass in this case would be equal to 8. There's kind of us just trying to think it through.
But what about situations where there's more than 2 weights?
Right, we're going to start with 2. I may give you the formula now. I just wanted intuition, and now I'm going to show you formula gives you intuition.
What if there's like a smooth gradient across the entire line.
One step at a time.
Okay.
Okay, so 2 weights. There's intuitively where you know it should be just by thinking about it. Here's how you get your center of mass in general. You're going to take whatever your first mass is, times however far over it is, plus your second mass, wherever it is, times however far over it is, and then you're going to just divide it by m1 plus m2. For those of you familiar with weighted averages, this is just a weighted average. You weight each weight by how far away it is.
So you're saying M1 would be 6 in that example?
Or sorry, you weight each x based off of how much mass it has there.
Okay.
Okay, so let's calculate this in this case. That would be 10 times 6 is
Oh.
60, plus 2 times 18 is
36.
36, and then 10 plus 2 is
12.
12. So 60 plus 36 is,
96.
divided by 12 is 8.
8.
66 divided by
96.
96 divided by 8.
Divided by 12.
Or sorry, it gives you 8.
Yeah.
Good?
8. Oh, okay.
Okay.
Okay. And if we had 3 masses, then you would just do this for all 3 masses. And if you have 4, you do it for 4.
I assume there's gotta be a zero here somewhere.
And if you have 5, you do it for 5. Well, we'll start out with just for finite. We won't worry about integrals.
There's gotta be one. It's just
Probably
screen
is.
right now.
Yes, we will calculate some centers of masses of some objects. And we'll have to come up with some sort of integral to do it. But for now, I mean, you can integrate all the positions times little dm for how much mass it has at that position. Okay. So, our x-coordinate then, our x-coordinate for our center of mass, you just take m times the x1 position plus the mass times the x2 position, dot, dot, dot. That's how you get the x center of mass. If we've got it in 2 dimensions, then to get the y center of mass, it's the exact same thing but using the y coordinates.
Are they separate from each other?
You can calculate them separately or collectively. In general, here's how you get the center of mass, and here's its definition. So the center of mass for some m particle system is going to be the mass of object 1 times its position vector, plus the mass of object 2 times its position vector, plus the mass of object 3 times its position vector, dot, 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 all the way through. Now, since these are vectors, you can break it up into its x, y, and z components. And what would its x component be? That would be m times x1 plus m times x2. It would be exactly this, but for all n cases.
Yeah.
Same for the y, same for the z. So yeah, you can break it up into each of its 3 components because it's a position vector.
That makes sense.
Good?
Yeah, that's.
So here's its center of mass, and it's just a weighted average. You weight each position by how much mass it has at that position. And then hopefully you're okay reading sums like this. Here's how I want to write it out. And I need you comfortable with some nation notation because we can't always write out like
Is
this.
that an I?
Yeah, so this is the sum for all m sub I times r sub I, where r is the position vector of the ith particle.
Yeah.
And divided by the sum of all m sub I things.
Doesn't that cancel out?
No, 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 no. You
What?
cannot just cancel out these masses with those.
They're big times.
I cannot
Oh,
take.
some.
Okay, yes, sum.
I read the.
I see the dot 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 is a product, or maybe you saw those.
I saw the 2 sums and I'm like, oh.
Okay. Can't cancel out sum, stop and bothering.
Right.
Now we sum up the masses in a system so often, that's a regular thing to do. It's typically what we mean by big M. So by big M, we typically mean the sums of all the masses. So it's the total mass of the system. You with me? Okay, so if that's the total mass of the system, that's the total mass of the system, and that's the position of the center of mass. What is the velocity of the center of mass?
What?
Here's the position of the center of mass.
It doesn't have.
How does velocity and center of mass equate each
Oh,
other?
is it like momentum kind of idea?
Well, how do you define velocity?
It's the derivative of position.
It's the derivative of position with respect to time.
Right. But how does that make sense to have a velocity for your center of mass?
It's how you can view the whole system as a whole moving.
So like that, right?
But just what exactly is the velocity of the center of mass? Well, it's just going to be the time derivative of this.
Yes.
It's just going to be the derivative of r of your center of mass with respect to time.
This is kind of painful.
Looks kind of painful.
I mean, it's all
Well, what's this one going to be? It's going to be m1 times v1 when we take its derivative.
okay.
What's m1 times v1?
That's your
Momentum.
That's the momentum of object 1.
Okay.
Plus the momentum of object 2. Plus plus the momentum of object n.
Yeah.
Which is just going to be, all over. I'm just going to write big M now for the sum of all the masses.
Oh, so momentum. Okay.
Good so far? Or in other words, it's just equal to your total momentum divided by M.
Okay. Where'd your metric go?
Oh, sorry. Thank you. These are all vectors, yes.
Alright, that makes sense.
Okay. Yep. Good. Good so far?
Yeah.
Now, the big drum roll, bring this over here. And so your total momentum is just equal to your mass times the velocity of your center of mass.
Your total mass.
Your total mass, the mass of the whole system,
Oh,
times the velocity of the center of mass.
that's
And so the momentum of the entire system behaves as though all the mass is located at the center of mass. What does this mean? I take some, we'll scribble down here for a second. I take some TNT, I light it, and I stick it in a cannon and I launch it through the air. So here's my stick of TNT and it's flying through the air. Well, right here in the air, it blows up. And now it's an explosion into just all sorts of gunk. If I were to follow the center of mass of all sorts of that gunk, it would follow the exact same trajectory that the TNT stick was following before.
but
The momentum of the whole system behaves the same as though it were all located with its center of mass.
But it won't ever reach that point. Like the whole gas won't ever reach the ending point. It'll stop way before that.
I'm saying that, let's say that doing our projectile motion calculations at TNT would have been right there, had it not blown up.
That's what center of mass.
I'm saying now, if you take the cloud, whatever it looks like at that time, and you were to calculate where's its center of mass, it would be right there.
Exactly.
The explosion did not change the trajectory of the center of mass.
But if you think about it, like when you shoot it up, it explodes. The explosion doesn't like continue to the ground. It like stops and then falls straight up.
Well, okay, now you gotta take into account air resistance and all the things that you have to take into account.
Right.
So, good.
Ignoring air resistance, it would.
Okay, take a stick of TNT in outer space, but it could still blow up. The fuse still works, and chuck it.
And the gas will follow that after.
And the gas will keep going as though it were all centered at that center of mass. And it will all behave as though all the mass were at the center of mass.
That's crazy.
This is why when you're looking outside the system, it's perfectly valid to just pretend that all the mass is at the center of mass and ignore how it's actually distributed.
Can you do that for like car crashes? Like collisions?
For calculating momentum, yes. And for trying to figure out how it's going to be moving after the fact, yes. Where it gets messy is when you start taking into account rotations. But yes, this is perfectly 100% valid.
That's pretty cool.
Rotation changes the center of gravity. Oh.
How mass is distributed changes how
It rotates.
you get linear, rotational momentum. Angular momentum. Jeez, that's what I was looking for. Angular momentum. We'll get to that. That'll be a chapter in like 2 weeks. But for now, ignore that. So, crazy result. You can treat it as though all the mass is at the center of mass. And same thing. I was trying to leave you side here. Mass times that is equal to the total momentum. Okay, that's what we were saying there. We don't need that as a circuit line, actually. So that will give us a little bit more space now with our acceleration. Once again, what is the acceleration now of our center of mass then?
Repeat the derivative of that.
That is going to be the time derivative of all these things. But what is the time derivative of momentum?
It's force.
It's the force.
It's not force.
Yeah.
Yes.
Oh, I'm thinking the integral of it. Which
And
is,
so now, when you take the acceleration,
what's it called?
you're going to get all the forces divided by the total mass.
Right, that kind of makes sense.
Where all the internal forces, once again, are going to cancel out just like they did over here. And you're going to be left with just the external forces.
So your acceleration is.
So this is going to equal the F external, the sum of all your external forces, divided by M. Or in other words, mass times the acceleration of your center of mass is equal to
The sum of your
the sum of your external forces. And so it, once again, acts as though all the mass were centered at the center of mass. And the whole system accelerates the same way that it would as if all the mass were at the center of mass.
What's the integral of momentum then? What was that word called? Integral momentum.
Impulse? What?
Impulse, yeah, that's what I was thinking.
We got our impulse from integrating force with respect to time.
integral.
An impulse is a change in momentum.
Yeah. It's not the integral.
You did integrate momentum.
Well,
Yeah.
And so when you take the derivative of momentums, that gets you forces. If integrating forces get you momentums, differentiating momentums get you forces. Remember, an impulse is just a change in momentum.
Yeah.
You can say it's momentums.
so it's just delta J, delta
P.
vector J. Right?
Your impulse vector is just your change in momentum vector.
Impulse. Okay.
What happens if we integrate momentum? Is that useful?
What happens if you integrate momentum with respect to velocity? And you'll notice that that gives you that 1/2 mv squared.
Oh, kinetic.
And so, well, there's a connection there, but ignore it.
How are we gonna, what?
Alright.
Alright, the way you are going to calculate kinetic energies is you are going to integrate forces over distances.
Yeah.
The way you're typically going to calculate momentums is you're going to integrate forces over times. Or do a force times a time. You can kind of think about that as the same thing.
Makes sense.
Okay, but we handled our center of mass conversation. I think I said everything I wanted to. Alright, so let's just start churning out examples. Do you need a break first? Alright, let's do break and then we'll do examples after.
Oh.
Alright, let's jump into example problems now. Using all these fancy equations. You throw a ball with a mass, so we have our mass is equal to 0.4
Yes.
kilograms against a brick wall. It hits the wall, moving with a horizontal velocity to the left. Let's call the left our negative direction. So we'll say V1 is equal to negative 30. And then rebounds horizontally to the right at 20 meters per second. So V2 is equal to 20 meters per second. And so our question is, find the impulse. So what is our impulse? It's our change in momentum. Our impulse is equal to our final momentum minus our initial momentum. Typically it's a vector quantity, but since this is one-dimensional, I'm just using signs to keep track of the fact that it's vectors. So our final momentum is what? 0.4 times 20 is?
4 times 20 is
5.
0.4.
Oh, wow.
2 times 4 is?
8.
Carry a 0.
80.
Wow. 0.8 with the 0 gives you 8, right?
Yes.
Okay, there's our final momentum. Minus our initial momentum. What was our initial momentum? What's 0.4 times 30?
12.
12. But minus negative 12 gives us plus 12. So our momentum ended 8 Newton seconds. Our momentum started out negative 12 Newton seconds.
You just times 0.4 by those two.
And so our change in momentum was 20 Newton seconds. Make sense?
Sure, crap, okay.
Because remember, momentum is a vector. It matters which way you're going.
Yeah.
Okay. And now, what was our next one? If the ball is in contact with the wall for that amount of time, so our small delta t here is equal to, is it 0.01 or 001?
0.
0.01.
1 0.
Then what is our average force? Now going all the way back here, our average force is equal to our impulse divided by time. One of the first things we talked about. So our average force is equal to our impulse divided by the time interval that we're talking about. Typically a vector quantity, right? And so what is this equal to? Well, divide this,
At
20 by 0.01 gives you 2,000. 2,000 newtons.
And so what is that saying? What's
That, so when you take the ball, and I bounce it off this wall, if it only made contact with the wall for 1/100th of a second, then the wall was exerting an average force of 2,000 newtons.
Okay.
So a big force, but for a very small interval of time, creating the acceleration that we need to change
And
it.
we lost 10 meters per second of velocity when we hit the wall. Right?
Yes.
So where did that energy go into, where did that energy go?
Where did the energy go? Just into the wall, and heating up the wall and whatever else happened there.
Is that like a normal amount of energy to have lost?
I have no idea.
Seems like a lot.
It would completely depend on the makeup of your ball
And the wall.
and your wall. Yeah, so it's going to be very material dependent.
Okay.
If you were throwing gum at a glue wall, you wouldn't expect any bounce back. If you were throwing a tennis ball at a brick wall, you would expect a lot more bounce back.
Yes. Okay, that makes sense.
So whatever it is, let's see. So 2,000 newtons and 20 newton seconds. That's what we got, right? All right, next, let's kick a soccer ball rather than throw it at a wall. So a soccer ball has a mass of 0.4 kilograms. That's the same as what we had before. And it's initially moving to the left at 20 meters per second. Oh, this is going to be a two-dimensional problem. So we got our mass. Let's see, our initial velocity. They probably have a picture for this really quick. Okay, there's our picture. So soccer ball coming in, it's getting kicked, and it's shooting off at 45 degrees after, right? So we'll go ahead and we'll set up our coordinate system same way they do, so x, y direction like that. X, y. What is our initial velocity?
-20.
Let's keep track of each component. It's going to be -20 for the x direction and 0 for the y direction, right? And what is v2 going to be? Our ending velocity. In our ending direction, what's its velocity in the x direction?
20.
No.
Cosine of 40.
Cosine
30 meters per second.
So 30 times cosine of 45,
Yeah.
right?
Yes.
For 30 times root 2 over 2 for cosine of 45. And same with for in the y direction. Good so far? Okay. Don't remember what the question was. So, a soccer ball, we have its mass. Initially, it's moving to the left at 20 meters per second, but then it's kicked. After the kick, it's moving at 45 degrees upwards to the right, 30 meters per second.
Find the impulse.
Okay, so we're looking for the impulse, so let's find the impulse. And the impulse of the net force, and then the average net force. Assuming the time, we already have our delta t. No, we erase that. Same delta t as before. So once again, our delta t is equal to 0.01, right?
Yes.
Okay. So, how do we get our impulse?
It's the integral.
It's going to be our final momentum minus our initial momentum. Right?
Okay.
And so it's just going to be This is just m times v1 minus m times v2.
Isn't it NV?
Or sorry, mv2, yes. I said it backwards, you're thinking right. Okay, so let's just go ahead and calculate that. So what is our impulse vector going to be? v2 minus v1, but then scaled up by m. v2 is
30 times.
30 square root of 2. So this is going to be, I'm going to do my m first, and we'll multiply it by v1, v2 minus v1. You with me?
15 square root of
30, oh, right. 15 square root of 2 minus negative 20. That will be its x direction.
You said minus, but row plus.
Minus
Mhm.
negative 1.
Minus negative is a plus.
Okay.
Okay, and then in here we're going to have m times 15 square root of 2 minus 0.
Yeah.
So there's our impulse vector. Let's go ahead and put some numbers in.
30 at minus 0. Oh, velocity. Okay.
Right. So just did this in the x direction and the y direction. Right?
Yeah.
Okay. So our mass was 0.4. So we have 0.4 times 15 times, oops, square root, yes, okay, square root of 2 plus 20. Did something weird. Okay, so this is equal to 16.4853. And then once again we have 0.4 times 15 times the square root of 2 is equal to 8.48528. Whatever. So, find the impulse of the net force and the average net force.
So we found the impulse.
So we found the impulse. I wonder if that's how they have it recorded. Okay, yes, they put it in the x and y direction. So in the x direction, they got 16.5, which is what we get when we round to the right number of significant figures. And then in the y direction, we get 8.5. I didn't write it that way because I thought they were going to have us calculate j, and so I was going to round when we actually just wrote the magnitude. But I guess that's not what they wanted.
And they want us to find the average.
Okay, so that was that part. And then next they wanted us to find the average net force,
Which is
right?
J over your time.
Which is J over your time. So let's find J now. What's J going to be? Just the square root of that squared plus that squared. It's just the magnitude of that vector.
You have, over there, it's an actual vector though.
Oh, right. So if writing it how we have it over there is this equation. I'll scribble up here. Right?
Okay. You have it as your force.
Oh,
Your,
that's supposed to be times.
yes.
Did I write it wrong over there, or did I just?
No,
Not
you're
just
right
over
over there.
Okay, so our force is equal to J over delta T, but the point is they point in the same direction. We're looking for the magnitude of F. The magnitude of F is going to be the magnitude of J divided by delta T.
Why are we looking for the magnitude?
How
How does that come out here?
the average net force, I assume that they want a magnitude. Maybe they don't.
The magnitude
Direction of
is-
magnitude.
So we should get the 1.9 times 10 to the third. Oh, they want direction and magnitude. Okay, so we'll find both. Okay, so let's start with the magnitude. So the magnitude of J, once again, is just going to be equal to the square root of that squared plus that squared. So we're going to do the square root of the first number squared plus the second number squared, all under the radical. And this is coming out to 18.5 Newton seconds. And now, to get our average force, just divide that by the delta T. our delta T was 0.01, right?
Mm.
And so our force average, its magnitude, is equal to, well, just 1850 when you round it. Just taking that and multiplying it by 100. Okay, and then our direction. Notice that the direction of this vector is the same as the direction of this vector. They're just scaled up versions of each other.
How was that obvious?
Okay, I'm going to rewrite this.
Okay.
Take that vector, scale it by that number. Scaling a vector just changes how long it is. It doesn't change its direction.
How do we know that F and J are in the same direction?
Because this equation is true. And so they have to be in the same direction.
Oh.
Because it's true, then they're in the same direction.
Yeah, the equation's saying that they're in the same direction.
Oh.
We're not saying they're in the same direction so the equation's true. We're saying since the equation's true, then they're in the same direction. They have to be.
Right. Because you're not actually changing.
Because if I told you A is equal to 2 of vector B, and you know that vector B is equal to the vector 1, 2, what is the vector A?
0.51.
And it's just going to be the vector 1/2, 1. Both those vectors point in the same direction.
Yeah.
They're just different sizes of each other.
Okay, that makes sense.
So scaling a vector just changes its scale. It doesn't change its direction.
Right.
Okay. So we can just use, the point of all that is, I can use these numbers to calculate the angle.
Yes.
And so the angle, now, that this is going to move at, did he give it a particular name?
No.
We'll just call it theta. Theta, that is going to be the arc tangent of rise over run of j sub y over j sub x. Good? And so, we do arc tangent of j sub y, oh shoot, that was my j sub x. J sub y divided by j sub x, and it comes out to 27.2 degrees.
So what's our physical interpretation of that?
I don't know why they only have 2. Our physical interpretation of that is when the kid is kicking the ball, on average, he was exerting, like the actual force that he's exerting in that time is extremely variable as he's actually making contact with the ball. It's all over the place. It's initially a force like that, then like this, and like this, who knows? But on average, he was hitting it with a force. If we were to add up all infinitely many of those forces, so we actually were to take the integral of the forces and then divide it by the displacement, that's how we get an average, right?
Yes.
So if we were to do that, then the average height of that function would be this vector at that angle. So on average, all of them were a force something like that. That's the average force he exerted in that time.
So why did the ball fly at a 45-degree angle instead of a 27-degree angle? Like what made the ball fly that instead of that force vector?
So you can almost think about it as what were all the average accelerations? There were some accelerations that went into changing its direction and some accelerations that went to giving it speed. And the forces had to apply all those. There's no way to just say what that should be.
Oh. Okay. Oh, that's pretty useful though.
So there's that problem. On to the next one. Example A4. Let's talk about this problem a little bit more generally before we do that specific problem. Going back to, I don't know, you go back 300 years ago. A common question was, if you were going to buy a firearm, how fast does it shoot out its bullets? How do you measure how fast a rifle shoots a bullet if you lived 300 years ago?
Measure its recoil.
Kinematics.
You get your stopwatch out,
And you're
you
ready.
say fire, and you see when it crosses a 100-yard mark, and
Actually, I would be hard.
So the
you guys say, where does it land? Well, how do you know that it just lands like that? Well, if it hits, rolls, tumbles, blah, blah, blah. How do you figure out how fast a bullet leaves a rifle? You exist 300 years ago.
you count it, and then
You count it?
kinematics.
On your finger.
And kinematics. Well, of course, you just integrate with the forces and do the maths, and it will come out.
Well, you know the math, you know all that.
So let's think how we would actually do this. So we've got our rifle here. However, we got our rifle.
Probably not.
There's our trigger, whatever. It's going to shoot some bullet out.
Uh-huh.
What we're going to do is we're going to take a block of wood and we're going to hang it from a string like a pendulum.
Let's see how far it moves.
Kind of. We're going to see how high up it goes. So we're going to shoot the bullet into the block of wood. And then that is going to cause the wood to rotate and to go up some distance. So drawing into the future sun, it's going to move it's like, should we try and draw it like a dotted? Here's where it is at some point in the future. There's like its future self. And it's going to go up some distance, h. And we're going to measure that height, and that's how we're going to determine how fast the bullet went.
How's
Let's do it.
Kinematics.
So, what we are looking for is the velocity of the bullet. Now, what can we easily measure?
the mass of the bullet?
We can easily measure the mass of the bullet. So let's assume that we know the mass of the bullet. What else can we easily measure?
The height of the...
Or
The mass of the block.
Oh yeah, the mass of the bullet.
Oh, sugar. Those are both B's.
block.
Come up with something clever for me.
Bullet. Boulder.
Wood. We'll call that the wood. Mass of the wood. Okay. The mass of the wood and the mass of the bullet. Good so far?
Yeah.
Okay. And now, let's just see what he gives us. The mass of the rifle. Oh, because we're going to do a kickback. We can also measure the mass of the rifle. We'll come back and do his problem, whatever his problem is, in a second.
Okay.
Let's stick with ours for a second. It's going to be related. And then finally, let's let's see, what else do we need? And then h, we can measure h. So h is going to be another number. And from this, we are going to try and figure out the mass of the bullet. Or sorry, the speed of the bullet, the velocity of the bullet. You with me? Okay, so what do I know? I know that the mass of the bullet times the velocity of the bullet,
Is your
that's going to be my momentum of the bullet right before it hits the block.
Square and then put 1 half.
No,
oh,
this is the momentum of the bullet. So I shoot my bullet out of the gun. Here's my bullet. So look at the momentum in my system right here. Gun's holding still, block's holding still, bullet's moving.
mm,
Bullet is moving, well, the gun's not really part of the system. Ignore this gun. So we just care about the bullet and the block. Right now, the bullet is moving with some velocity that way, really fast, velocity of the bullet, and it has its mass. What's the momentum of the block?
0.
0. Afterwards, the bullet is now embedded into the block, and the block starts moving that way.
Yeah.
And so this has to be equal to the mass of the bullet plus the mass of the block, or the wood, times the velocity of the wood.
Yeah. It's the Inelastic.
It's just saying, yeah,
Oh.
it's just saying that the momentum at the beginning, when the bullet was out here, is equal to the momentum when the bullet's ingrained into the block. The momentum didn't change.
Yes. Conservation of movement.
You with me so far?
Mhm.
So those two have to be equal. Now, what is the kinetic energy of the system when the bullet goes into the block?
When it hits it, 0.
No.
Kinetic.
It's
The kinetic energy of the block, once the bullet goes in there,
it's velocity.
is going to be 1/2 the mass of the bullet plus the mass of the wood times the velocity of the wood squared.
Is that mass of the bullet large enough to be
We'll keep it in there.
The
It won't
velocity
change
is
anything
zero.
that much.
Velocity of the wood is 0 before it hits.
No, okay, so this momentum, this was before the bullet was in to after the bullet was in.
Yeah.
This is bullets in the wood,
How fast will it be?
right when the wood starts swinging. So, what we're going to do now is I'm going to write out this equation. U1 plus K1 plus W is equal to U2 plus K2. Where now R1 is going to be the instant the block starts moving because it has the bullet in it, to when it reaches its highest point in the air and stops going up and starts coming back down.
Wouldn't it be more of acceleration than velocity?
We're just tracking the energies.
Okay.
So what is the kinetic energy when the bullet first goes in there? Or sorry, what's the potential energy? We'll call this Y equals 0, however high it is. So its gravitational potential energy is 0. Its kinetic energy, right there. Work being done on the system, 0, is equal to, what's the potential energy when the block reaches its max point?
MGH.
MGH plus, what's the kinetic energy when it reaches its highest point? 0. It's not moving once it reaches that peak point. With me?
Yeah.
So there are our equations. 2 equations, 2 unknowns. What don't we know?
We don't know the velocity of the wood, and we don't know the velocity of the bullet.
Yeah, we don't know the velocity of the wood, and we don't know the velocity of the bullet. So we need to solve the velocity of the wood in one equation and substitute it in to get the velocity of the bullet. Good?
Yep.
I think I'm going to use this one, maybe, to get the velocity of the wood first. Because I think I see something pretty nice. So first, notice I can cancel those out both sides and bring the 2 over. So I'm going to get the velocity of the wood squared is equal to 2gh. Square root both sides, and we get velocity of the wood is equal to the square root of 2gh. Okay, so that's the velocity of the wood. Now bring that up here, and I can get the velocity of my bullet. So now the velocity of the bullet is equal to mb plus mw, the total mass, whatever that is, times the velocity of the wood, all divided by the mass of the bullet.
Which is a really small number.
Right, so we're going to get a really big velocity for our bullet,
Which makes sense.
which makes sense. And so that's how they did it. Okay, so now we'll figure out whatever they're talking about. Maybe they had us do this on a later one.
I don't think there's anything there.
Could you do it if it was like a spring loaded piece of wood so that it just indents the spring instead of
And you see how far it compresses a spring?
Oh, yeah, you do.
Yep, it would be the exact same idea. You just need the wood to shove it into some potential energy system. That's a function of displacement.
Can you do it off the recoil of the rifle?
Can you do it off of the recoil of the rifle? Yes. But the recoil of the rifle is something that's very hard to measure.
Especially because the mass of the bullet is small.
Right, so it's going to have that same momentum. But also, conservation of momentum, you just brought something to my mind, has nothing to do with this problem. Just one of the things that bugs me in movies. You watch a guy with a handgun and he shoots someone and they get knocked over by the bullet. The momentum they feel from that bullet is the exact same as the kickback from the gun. That's how hard the bullet hits you, how much momentum it puts into your body. If the kickback from my gun doesn't knock me over, then the bullet can't knock you over.
So what about the real things where they'll shoot you and your limbs will split out? Like a super
Oh,
hard
it can tear you apart. It's a lot more pressure.
Yeah.
So with the kickback of the gun, that's a whole gun, whereas a small bullet, that's going to have a lot of pressure, and yeah, it's going to break things inside of you, but it's not going to knock you over, unless it can knock me over.
And some guns can do that.
Right, but, you know, a little handgun, you watch the cop shoot the bad guy and he goes flying over.
Yeah.
Yeah, it doesn't work that way. Or that cop just has an amazing grip. Just a tough guy.
Does this just change the way you watch movies now?
Knowing physics?
Yeah.
Yes. It changes the ways you watch movies. Okay. So whatever our problem is. A marksman holds a rifle with a mass MR, so we know the mass of the rifle. Holds it loosely so it can recoil freely. He fires a gun, the mass of the bullet is 5 grams horizontally. What is the velocity relative to the ground of the bullet? Oh, sorry. That is the velocity. What is the recoil velocity of the rifle? Okay. So we have the mass of the rifle. First off, before I shoot the gun, what's the momentum? 0. So the momentum at the start has to be 0, is equal to the mass of the rifle times the velocity of the rifle, how much it bounces back at me. So the velocity of the rifle is going to be negative, plus the mass of the bullet times the velocity of the bullet. And so how do we find the recoil velocity?
Does that x mean just x?
Move that to the other side and divide by the mass of the rifle. So the velocity of the rifle is just going to be negative, moving that to the other side. Mass of the bullet times the velocity of the bullet divided by the mass of the rifle.
It's just x direction is what it's saying.
Yeah, so it's all happening in the x direction. We're not going to keep track of all those sub-x's. And so here's how we do it. And so in our specific case, the mass of the bullet, what was that?
5 grams.
So 0.005 to get to kilograms.
Yeah.
Times, the velocity of the bullet was 300 meters per second.
All over 3.
Divided by 3, and you get a whopping 0.5
0.5 what?
meters per second.
Which kind of makes sense.
So it kicks back with 0.5, I don't know what our significant figures is, 3 significant figures?
Yeah.
0 meters per second. Okay.
Shouldn't that be 0.50?
Half a meter in a second.
Oh, negative, because negative. So it's traveling that way at half a meter per second.
In 1 second, you grab a half meter. That is awesome.
Well, that means if I had the gun if I take the gun in outer space and I push the trigger, so it shoots, the gun will start traveling that way at half a meter per second, as a bullet travels that way at 300 meters per second.
So 2 seconds of travel meter.
Yeah, ish. Okay.
That makes total sense.
Okay.
Travel 3B, same
But people actually shoot that, and that number does not seem right.
Well, they're exerting an acceleration and they're stopping it.
Your shotgun.
Yeah.
There's been a lot of kickback.
Well, it depends on the gun. It doesn't have to have a lot of kickback though. Stopping, if I initially give it a speed of half a meter a second, how hard is it for you to stop that? It's not very fast.
It's not.
So it's easy for you to control. Half a meter in a second.
It's pretty quick.
Half a meter in a second is pretty slow.
Yes. I mean, that's 3B if you say.
Half a meter per second is a little faster than a mile an hour.
Yeah.
Okay.
Like, well.
Okay. Anyways. There must have been a second part because I saw some other numbers.
No, there's no one.
What is the final momentum and final kinetic energy? So, what is the final momentum? It's 0.
Of them.
A momentum of what?
Oh, of the bullet and the rifle. Okay, so they want it separately. So the final momentum of the bullet, I don't know what it is.
Mass times velocity.
So we'll do this one really quick. The velocity of the rifle times what was the mass of the rifle?
It was 3 kilograms.
3 kilograms.
3.
It's a light.
So this is going to be negative 1.5 Newton seconds. This is going to be positive 1.5 Newton seconds in terms of its momentum. Kinetic energy. What's the kinetic energy? How is the kinetic energy of the rifle going to compare with the kinetic energy of the bullet?
They're going to be very different.
Very different. Shouldn't they both have the same amount of energy? The energy going this way has to be the same as the energy going that way, right? So the kinetic energy of the rifle, let's find that, and the kinetic energy of the bullet. How do we expect those to compare?
The kinetic energy of the bullet is way higher.
They should have the same kinetic energy.
Why?
Because they shouldn't. I was just trying to get to ability or intuition. Couldn't think of anything off the top of my head. Okay, they're going to be very different. I was just seeing if I could trick you. Okay. So, the kinetic energy of the rifle is going to be 1/2 times the mass of the rifle was 3 times the velocity of the rifle, 0.5 squared, comes out to 0.375 joules.
Which
A third of a joule. That is a nothing.
makes
On the other hand, the bullet, let's see, 1/2 times the mass of the bullet was 0.005 times the velocity of the bullet was 300
yeah.
squared, comes out to 225 joules.
That still seems to go a little low.
So this has like 600 times as much energy as this has. Same momentum, very different energies.
Right.
What was the momentum?
It was there.
The momentum is negative 1.5 for the rifle, positive 1.5 for the bullet.
Oh.
Okay, there's that one. Did they really not do the gun one? I was gonna jump to the gun one. That's a pretty standard one to do. Oh yeah, here it is. So, a ballistics pendulum. So figure 8.18. Here it is, you got the mass of the bullet goes into the block of wood and you measure how high it goes. So this one said, let's read exactly what the problem says. That figure showing basically this, shows a ballistic pendulum, a simple system for measuring the speed of a bullet. A bullet of mass B makes a completely inelastic collision, so it gets implanted in the wood, with a block of wood with mass NW, which is suspended like a pendulum. After the impact, the block swings up to a maximum height Y. We used H. They're using Y. In terms of Y, mass of the bullet, mass of the wood, what is the initial speed of the bullet? So here's what we found, the speed of the bullet. Now, let's go look at their solution just to make sure we didn't do anything wrong.
Oh crap.
Oh, they didn't substitute out their V2 yet. That's not the full solution.
Oh.
Okay. They used V1, we used velocity of the bullet. Same exact thing. So we didn't mess up.
Cool.
That's cool.
Okay. So, just wanted to do that one before I erased it because I thought I remembered reading that in the book. Okay, we did that. Let's do collisions with gliders. Let's do a two-dimensional one. Does this one have a picture?
Yeah.
That's a one-dimensional one. Let's find a collision with 2 dimensions so that we can
It's a little low. Yeah, there you go.
collision in a horizontal plane. All right, let's do this one. Okay, perfect. Maybe zoom out a little so that we can see more of it. You guys okay with skipping up to this example problem?
Yeah, no problem.
I feel like the collisions are pretty similar, so I just wanted to find a harder one.
We still need to do the rocket thing.
Oh yeah, we still need to do rocket time. Okay, so we've got some object A traveling with some initial velocity, and it's going to collide with this object. They're going to bounce off of each other, and we're going to have to figure out how they're bouncing off. So let's see the information it gives us. So the figure shows 2 battling robots on a frictionless surface. Robot A with a mass of 20 kilograms. So we know the mass of A is 20. And it initially moves at 2 meters per second parallel to the x-axis. So the velocity A initial is equal to 20 and 0, right?
Yeah.
It collides with robot B, which has a mass of 12,
Yeah.
and is initially at rest. So VB1 is equal to 0, 0. After the collision, robot A moves 1 meter per second in a direction that makes an angle 30 degrees with its initial direction. I don't know if that's up or down. Okay, alpha is up. So it's going to have a positive x and a positive y. So basing it off of their picture, then for object A, VA2, it's going 1 meter per second at 30 degrees. So what's its velocity in the x direction?
Cosine.
Cosine.
Cosine of 30. 1 times the cosine of 30, which is just cosine of 30. What's the cosine of 30 degrees?
Root 3 over 2.
1/2.
Nice try.
No,
Sine of 30 degrees, 1/2.
it's 1/2 root 3.
Okay, so that is our final velocity for object A, and I'm guessing we're looking for our final velocity for object B.
Yeah.
What is the final velocity for robot B? So what we are looking for is VB2. What's that equal to?
Kinetics time.
This one we're just going to use conservation of momentum, so we're not even using conservation of kinetic energy. So, what is our momentum in the beginning in the x direction? Let's do this in the x and y direction.
There's a P
V
station there.
and
There's a P station.
Vx.
So it's
MVAX.
So this is MA times 20.
Yep.
And that has to be equal to our momentum in the x direction at the end, which is going to be MB times
VB2.
well, what we're looking for.
VB2x.
I hate using all these subscripts, but shoot. Yeah, we're gonna have to do it.
It's so confusing. Which
VB2x plus MA, I'm not sure why I didn't do A first. MA in the x direction after the collision times square root of 3 over 2.
where are you getting the rest of
So the mass times the velocity of this plus the mass times the velocity of this in the x direction has to be equal to the mass times the velocity of this in the x direction and the mass times the velocity of this in the x direction. Oh, sorry, this is this one. This is this one.
Yeah.
This is object B, that's object A.
So what's your MA?
I should have written it that way. Let me do it this way. What is the momentum in the x direction of this object after the collision? It's its mass times its velocity in the x direction. Its mass times its velocity in the x direction. VA2 in the x direction, root 3 over 2.
Yeah, I'm saying where did you get that MA times 20?
Plus MB2. Oh, this one?
Yeah, where's that from?
Its mass times its velocity in the x direction.
Which is
For up
just
here.
one object.
In the x direction, we have MA times 20 plus MB times 0
Oh.
is equal to MA times the square root of 3 over 2 plus MB times VB2x. Whatever this number ends up being, we don't know yet. That's what we're solving for. And so we can use this equation to get the velocity of B in the x direction. So what is VB2x?
VB2x is.
It's going to be equal to, this is just 0. So I'm going to move this over here.
By division.
That's subtraction.
I'm going to subtract this over here and factor out the MA. And now I need to divide by MB. You follow all that?
Yeah, could you divide MA and
No.
you can't divide?
No.
Oh, because it's addition.
Yeah.
Okay. So, whatever that comes out to. Let's plug it all in. We have MA was 20. 20 times 20 minus square root of 3 over 2, all divided by MB was 12. And I got 31.89. I don't know if we'll ever need that rounded value later. Do we only have 2 significant figures? Or do we have 3? I'll pretend it's 2. Instead, this is 32 in the x direction. we do that right? That is a very different number. 2 meters per second.
Oh,
Okay. That'll make a difference. Okay. Let's try that one again. So, we've got 20 times 2 minus square root of 3 over 2, all divided by 12. Comes out to 1.89. If we do 2 significant figures, it's just going to come out to 1.9.
I think we do 3.
2, 2, 2.
The answer is 3.
Well,
It's always 3.
then they're wrong. 1.9. Okay. So there it is in the x direction. Now let's find it in the y direction. In the y direction, what's our momentum?
Just cosine or sinus.
No.
What's the direction? What's the momentum in the y direction for that?
0.
0. That.
Momentum
Zero.
in the y direction. Y. 0.
So 0 is
What's this thing's velocity in the y direction?
It has to count the angle.
Times its mass gives you a 0. So we got 0 plus 0 has to be equal to
5.
this one's velocity or momentum in the y direction
1/2.
is going to be ma times its velocity in the y direction is 1/2 plus mb times its velocity
E2y.
in the y direction.
Which is going to be negative.
So vb2y is going to be equal to, move this to the other side, so we get negative 1/2 ma time, or divided by mb, right? Because the mb would be over there divided out. So 1/2 times ma over mb. And so we get negative 0.5 times, is it 20 over 12 or 12 over 20? 20 over 12. So 20 over 12, negative 0.833333. So this is equal to negative 0.83. Negative 0.83. Okay, so if they wanted the magnitude, that's the vector. I assume that they wanted the magnitude. So VB2.
B is about 2.1.
Huh? It's going to be the square root of the x squared plus
Negative
the y squared. And I'm getting about a 1.7, 1.69, 1.7.
They did 1.89.
Oh, do 1.
It did negative of it squared, so it subtracted. My calculator did it done.
What?
We can't trust calculators.
You just have to make sure it's doing what you want it to do. So we want that squared plus that all squared. Okay, 2.06 rounds to 2.1. So this comes out to 2.1 meters per second, which is what they've got, right?
Yeah.
And then the direction is going to be the arctangent of y over x. So now we do arctangent of y divided by x. And we get negative 26. So theta is equal to minus 26 degrees.
Their answer was negative 24. Is that because they're 1.89 and not 1.9?
Yeah, probably. Because they're cheaters. Actually, they did it right because we rounded it.
Oh, I used a 1.69. Where'd that number even come from? I pre-selected wrong one when I did the arctangent.
Oh,
So that was me plugging in the wrong number.
okay.
So arctangent, my negative 0.83 divided by Not the 1.69, the 1.8891, right? Okay. Now it comes out to negative 23.7, which is negative 24. Alright. So there she is. So there it was in two directions. We did that. Should we go to rockets?
Yeah.
We should
All right.
do examples.
You're outvoted. Let's switch to rockets now. We did some examples, but we did more than the examples in the lecture. We just did it all general.
Right.
And so your example problems,
Should be easier.
you would be able to largely use those equations to solve.
We
So,
only did the first two sections of the examples.
huh?
We only did the first two sections of the examples.
Oh, and I also didn't do your hardest homework problem.
How are we gonna do something?
Next time you're going to get to class on time, so we have more time.
Yes, yes. That 5 minutes.
5 minutes.
All right, let's go over rockets, and then we'll at least do the hardest homework problem. Okay, how does a rocket work? We are going to come up with our own rocket ship in a very stupid way.
Okay.
Here's what we're going to do. We're going to be sitting in the back of a sled on a frictionless I-surface, and it's some big sled. And inside this big sled that we're sitting on, there are just a bunch of big balls. Bunch of balls, maybe not big balls, just a crap ton of balls. We'll say there's 1,000 of them. So we'll say there's 1,000 balls, and then us plus the sled are going to be 200 kilograms. So the whole system has 1,200 kilograms. You with me? Altogether, we have 1,000 balls, each weighing 1 kilogram. Now, what we're going to do on this frictionless surface is we're going to grab a ball and we're going to chuck it out the back.
We're gonna throw them.
And let's say we're going to throw the ball at 10 meters per second. You with me? So, what's the momentum before we throw the ball?
0.
0. So, once I throw the ball out, the momentum has to be 0. And so, the mass of the ball that I throw it times its velocity of the ball
Wait, it has
has to be equal to the mass of the sled times the velocity of the sled. In other words, those two things added together have to be 0. Maybe that's a better way to say it.
Why?
Because the momentum has to be 0. What was the momentum before I threw the ball?
0.
So the momentum after has to equal the momentum before.
Combination of
None of the internal forces increase the momentum. Throwing the ball is an internal force.
You with me so far?
Yeah.
So if I throw the ball out this way, then we're going to move that way a teeny bit,
Yes.
right?
Yeah.
So if I throw the ball out that way at 10 meters per second, that's negative 10 meters per second. We'll call that the positive direction. And this is 1. So this is negative 10 plus the mass now of our system, if we threw one ball out, is 1, 1,
9.
or sorry.
Yeah.
Oh, no, I did that right. 1199 times now the velocity of the sled.
What is one? Oh, you have 2,000 balls in there.
We had 1,000 balls, and then us plus the sled is another 200 kilograms.
Oh.
So 1,000 balls plus us and the sled is a total of 1,200 kilograms. So now, notice that we lost some of our mass by throwing a ball out. And what now is the velocity of our sled? The velocity of our sled is 10 divided by 1199,
Yeah.
right? And that comes out to, what does that approximately come out to? One of you got a calculator on you?
Okay.
It's going to be like 0.01 meters per second, a little bit slower.
0.008.
0.008 meters per second. So that hardly even moved us,
Yeah.
right?
Yeah.
Now, if instead I would have thrown the ball out the back at 1,000 meters per second, I've got a crazy strong arm, then what would have happened? This velocity of E would have been negative, what did I say, 1,000?
Yeah.
Or did I say 10,000?
10,000.
Okay, so that would have been negative 1,000, right?
Uh-huh.
Now when we solve for Vs, what would Vs in that case be?
1,000 over.
It would be equal to 1,000. We should have just done 800 balls and made the total thing 1,000.
So just 0.8.
Over 1199, which in this case is going to be approximately
48.
Or
0.8.
0.8 or 8.
0.8. So now it's almost going a meter per second. So the faster I throw that ball out, the more speed it added to us. Right? And then I throw another ball out, it's going to give us even more speed. I throw another ball out, it's going to give us even more speed.
Because your mass gets better every time.
Well, because it's just restart the problem now.
Alright.
And then restart the problem again, restart the problem again.
But every time you throw a ball, your mass is.
Initially, pretty much every time I throw the ball, I'm adding 0.8 meters per second.
But by the time you throw your last ball, you can have a lot.
So yeah, the mass gets less and less, so actually each throw is giving me a teeny bit more than 0.8, and it's gradually growing how much speed I'm getting each time.
By the time you're throwing your last ball, you're gaining 1,000 over 200.
Right, so by the time I throw my last ball, I'm gaining 5 meters per second.
5 meters per second.
Yeah, so it's getting gradually grow, so my last ball is adding 5 meters per second as our object's getting lighter and lighter.
Yeah.
Make sense?
Yeah.
So 2 things. The more mass I throw out, the faster we go. And the faster I throw the mass out, the faster we go.
Yeah.
So 2 basic.
So now, imagine we get crazy with this, and we rig up a TNT system to blow all those balls out of that sled at a crazy high speed.
Like all at once.
Well, all at once, or maybe we get some really strong cannon to keep shooting them out at really high speeds. Then that's going to give us a ton of thrust. This is intuitively how a rocket works. How does a rocket work? It has fuel, which has mass. It burns that fuel, which creates the explosion, and shoots that gas out at extremely high speed. And so even a small amount of mass going at a high speed can make a considerable difference to your velocity.
Yeah.
Good?
Yeah.
Trying to establish some intuition.
It makes sense.
So, here's our scenario. Here we are flying around in our rocket ship, and we're moving at some velocity v. Now, after some arbitrarily small amount of time, dt, what happened? How did our system change?
You lost.
Our mass changed by some small amount dm.
Lost weight, right?
Yeah, we lost weight. So dm is going to be a negative value. So negative dm is going to be what's shot out as fuel. Right? Because those are actual gas atoms. They're like a bunch of little teeny balls shooting out.
Shouldn't the negative DM be positive and the positive?
So
be
we have positive mass down here. dm is a negative quantity. Keep in mind, dm is less than 0. Our change is down, not up.
Okay.
So dm is our change in mass. So we have the negative of our change in mass coming out as fuel.
Oh, because positive.
So it's positive.
Yeah.
Good so far? Our velocity then, our new velocity is going to be our initial velocity plus a small change to our velocity, whatever that is. And the velocity of the fuel that it shoots down with is going to be the velocity of our rocket minus the exit velocity, like if you were standing on the edge of the rocket, how you see the gas shooting out. So that's what this is. This is how we see it shooting out. We see the rocket shooting up and the fuel shooting down. This is the velocity if you were sitting at the end of the rocket watching it shoot out.
Yeah, it makes sense.
So if our velocity of our rocket is, if the rocket's traveling faster that way than what we're shooting the fuel out with this way, then our exit velocity, then the total velocity that the fuel looks like it's going to have is going to go up. If that number is bigger than that number. On the other hand, if the exit velocity is bigger than that, which it's going to be, then it's going to actually look like it's shooting down.
Making it go up.
Okay, so velocity that we see the fuel shooting out with, the velocity of the rocket minus the velocity that actually shoots out of the rocket with. Okay, so now momentum is conserved from here to here. Only internal forces. It's out in outer space, no gravity, no nothing. So momentum's conserved. So P1 has to equal P2. What's our momentum down here?
Whatever it is.
mv. What's our momentum here now? Tracking all the same mass that we had before. going to be the momentum of the rocket, which is m plus dm, our new mass,
D meaning what?
times dm. dm is our small change in the mass.
Okay.
In this case, it's a negative quantity.
Small change in
It went down a teeny bit.
with the snowball throw, or the gas particles out.
Yeah. So dm is like, well, negative dm is like how is the gas leaving? That's exactly what it is.
Okay.
Okay, so we have the momentum of the rocket ship plus the momentum of the fuel.
Mm-hmm.
Good? Now just going to multiply it out. mv dm times v is vdm. mdv dm dv v negative dm negative vex negative dm. Good? Now notice those cancel out. Those cancel out. Good so far? Okay. And now, we have just those three quantities. There they are. I'm going to solve for mdv, so I'm going to move these to the other side. So mdv, move those to the other side, just makes them negative. Now, what is dm times dv in our limit?
Change in velocity's position.
An arbitrarily small change in mass times our arbitrarily small change in velocity is going to be 0 when we take our limit.
Yeah.
Okay.
It's like when we did the limit of 2n over 5n, if you were to then go add on something over n squared, it's not going to change anything.
Yeah.
This piece doesn't contribute anything in the limit because it's way, way smaller than these comparatively. And so when you take the limit, you still get 2/5. It doesn't matter that you added that little piece. So it's going to be that same kind of thinking. But we actually did use similar thinking when we talked about differentials back in calculus.
Yeah.
Anyways, so that term goes to 0. It is 0 in the limit, but if you're talking about arbitrarily small values, it's approximately 0. And so this is approximately that. But in the limit, it's exactly that. So I get mdv is equal to negative vex dm. With me so far?
Okay.
Take the derivative with respect to time on both sides. What is the derivative of v with respect to time?
Acceleration.
Acceleration.
Acceleration. What's mass times acceleration?
Force.
Force. And that's what we call thrust. So there we go. That's how you calculate the thrust of the rocket.
Your exit velocity times your,
It's how fast the mass is shooting out of the back
and how fast your
times the change in mass with respect to time. So the more balls I throw out every second, the faster we go. And the faster I throw the balls out, the faster we go, the more thrust I generate.
So if I wanted to actually calculate that, I would need like figure out the chemical properties of it or what?
It will tell it to you. So the problem will tell you it has an exit velocity of this, and assume it's dropping down like however. So it will give you the quantities to plug in. I don't know if they'll give you mass as a function of time, and you have to figure out the change in mass with respect to time. That could happen, but
He wants to be a rocket science, so.
anyways, there's thrust.
Mm.
Now we're going to also come up with a velocity equation, so we can talk about the speed of this at any given time.
Okay.
Or, I guess it's going to be at any given mass. How do you find the velocity now from this? So here's our force. Once again, resetting up what was our acceleration. So, notice, here's our force. Divide this by m. Divide both sides by m gives us our acceleration.
Yeah.
Yeah.
Divide both sides by m gives you the acceleration. Good so far?
Yeah.
Acceleration is dv dt. So I just replace acceleration with dv dt. Now, we do our cheat and we multiply both sides by dt.
We integrate with respect to time.
And then we integrate it from time 1 to time 2. And so integrate that from time 1 to time 2, integrate that from time 1 to time 2, and what do we get? Our velocity at time 2 is usually what we mean by v at our final time, minus our initial velocity at time 1.
Yep.
Is going to be equal to, over here, the exit velocity, we're assuming is just a constant. We're going to assume your rocket maintains the same exit velocity as it shoots out the gas. Pretty normal.
You can't throttle though, with that would change that, I assume.
Huh?
Throttling your fuel would change your exit velocity.
I assume that you can change the rate at which it's burning. We'll say that you've got it at some constant burn.
Okay.
And then, this is just, what's the integral, maybe I shouldn't have written it that way. What's the integral of 1 over x dx equal to? Natural log of x, perfect. And so if we're doing this from time 1 to time 2 for our mass, and it's just going to be our final mass minus our initial mass, natural log. And a natural log of a difference, oh, sorry, now I'm going to plug in the negative here.
Yeah.
Plug in the negative, and that swaps the order that you take a difference. So plug in that negative, swaps the order, and now the difference of a logarithm is the quotient. A difference of exponents is a quotient of the numbers.
Yes.
When I say 2 to the 5 minus 3, that's the same thing as 2 to the 5 over 2 to the 3. A difference in exponents is a quotient of the numbers. Taking a log is an exponent. So that's an exponent, difference. The numbers are what you have inside.
Yes.
Okay. And there we go. There's our velocity equation. So your velocity is equal to your initial velocity plus the exit velocity times the natural log of your initial mass divided by your current mass. And this is assuming, I think this is assuming a constant burn rate.
Yeah.
We
But
won't
I'm not
need to
positive.
derive this, will we, for homework, or?
No, you'll just be using largely this equation and this equation.
Okay, because I got lost on there, but
No, we won't force you to derive any of this. Okay,
it's not going to appear on the test.
now let's do your hardest homework problem.
For the next lesson or for last lesson?
For the next one, we already did last lessons.
Yeah.
Last lesson wasn't bad at all.
It's never going to be bad if I'm doing it. It's only bad when you have to do it.
Yeah.
Well, I'm saying solving last week's homework was actually.
So I remember it was 101.
How do you determine the hardest one?
It has the 3 points.
3-star, and then it says chem or something like that, bio.
So 8.101. Neutron decay. A neutron at rest decays, which means it breaks up, to a proton and an electron. Energy is released in the decay and appears as kinetic energy of the proton and electron. The mass of a proton is 1,836 times bigger than the mass of the electron. So,
Chem.
the mass of my proton is 1,836, is that what's that? Times the mass of my electron. 1836. Oh, I should remember that. 1836, just doubles, okay. What fraction of the total energy released goes into the kinetic energy of the proton? Okay, so before, initially we have just a neutron sitting here. Nice, happy guy. After the fact, we have a proton shooting off one way, and our little teeny electron shooting off another way.
Wait, so the neutron is split up?
Yeah, it decays into a proton and electron.
How?
They decay.
Photosynthesis.
Everything eventually decays.
What are protons decaying?
Eventually everything will decay into photons.
Oh, okay.
But
It's inevitable.
you can think about how you create a neutron is you force a proton and electron together.
Okay, I didn't know that.
And then
Which is why
they can split and decay into a proton and electron, and they'll just randomly do it. There's a probability that it will do it in some given amount of time. It's kind of like a half-life for an atom. An atom will eventually decay and break up into smaller atoms.
I thought that was only for radioactive atoms.
Everything's technically radioactive. We just mean radioactive like it has a chance of hurting us.
Oh. Weird. Okay.
So I just have to.
like everyone's active. Just
Okay, so anyways, before, after.
Yeah.
Okay, what is the momentum before?
Zero.
Zero. It's just sitting there.
Zero.
So 0 is equal to, afterwards, I have the mass of my proton times the velocity of my proton plus the mass of my electron times the velocity of my electron. One of those velocities is going to be negative, one's going to be positive. So it's going to cancel out to 0.
Okay.
Good?
Yeah.
Now,
Wait, is that a vector quantity? Pretty close.
yeah, but we can view it as a one-dimensional problem.
Okay.
And so I'm going to randomly pick, let's say that the electron went this way, proton went this way. And we'll just say whichever way the electron's going is our negative direction. So we're keeping track of all our vectors. Good so far? And so, not sure which one we want to solve for which. It wants us to say what portion of the kinetic energy went into the proton.
Okay.
Right?
Yeah.
So I want to look at my proton's kinetic energy over my electron's kinetic energy.
How much of the proton's energy went to the electron?
How much kinetic energy went to the electron versus the proton? Right. Well, we're looking at the ratio of them.
The ratio, so the percentage.
So what is the kinetic energy of the proton?
It's the mass of the proton times the velocity.
It's 1/2 the mass of the proton times the velocity of the proton squared.
Okay, yeah. So
All over, what's the kinetic energy of the electron?
1/2 me squared. M sub e times v sub.
Now we see that the 1/2 go out, right? So mp times vp squared all over me times ve squared.
We know the mass of the proton is in terms of the electron,
Oh, yes, thank you.
so we can set that out.
So,
The MEs cancel out.
let's also, so I know mp in terms of me, but I also need to use this, and let's find vp in terms of ve.
Why do we need VP?
So that we can.
Well, I just need to cancel out terms. So if I get vp in terms of ve, I'll be able to cancel out my ve's.
Oh, yeah.
And if I get mp in terms of me, I'll be able to cancel out my me's, and I'll be left with the number, which will give me my ratio. Right?
Yes, yes.
So I already have mp in terms of me, so now I need to get vp in terms of ve. So what is vp? Move that to the other side and divide by mp. It's me times ve all over mp, where mp is equal to this. So it's equal to ve all over 1836.
What? Oh, yeah, okay. Pretty simple.
Everyone good? Okay, so let's make these substitutions now. So mp is 1836 times me times vp is
VE over 18.
ve squared over 1836 squared, right?
All over ME.
All over me times ve squared. Now one of these cancels out with that.
One of what? Oh, that's how that works?
Yes.
Okay.
Yeah,
So
I guess so.
it's squared.
one of that cancels with one of those.
Yeah, it's just.
So that gets rid of that, and that gets rid of that. Dividing the numerator is the same thing as sticking on the denominator. So this is going to be, don't want to do too much in one go, but hopefully you can follow this. Me times ve squared all over 1836 times, bringing that down, me times ve squared.
Oh, but it's the same thinking that allowed you to cancel it, right?
So there we go. So what is 1 over 1836? Want to calculate that really quick? And this was 8.11. Let me check the answer.
5.4 times 10 to the negative 4.
One sec. Where's the answers? Chapter 8, 101, right?
Yeah.
Chapter 8, 101. They have 0.0544%. So they said 0.0544%. 5.44%. Read me what you have.
5.4 times 10 to the negative 4.
5.4 times 10 to the minus 4,
Yes.
right? And so minus 4, that would be shifting it 4 times. 1, 2, 3, 4.
Yeah.
And then
0, 0, 0 point. If you make a percent, then you start right there.
Yes.
So same thing.
Sweet.
All right, so we did it. There's your horse props.
So easy when you do it.
Yeah.
Yeah.
Okay. Kind of out of time, so we'll call it there. I want your guys' tests.
Oh, yes.